There is a quiet strangeness to the passage of time. A single hour can feel like a minute. A minute can stretch into a lifetime. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. It is a familiar feeling. The endless afternoon meeting where the second hand of the clock seemed to stop moving, each tick a small eternity. Now, compare that to a truly great conversation, one that went so late into the night that the sun began to rise unnoticed, where 5 hours disappeared in what felt like a single breath. A childhood summer can feel like an entire, self-contained epic, stretching out in a golden, infinite haze. And yet, the last 5, perhaps 10 years, have flown by in a blur. This is not a story about what a clock says. It is a story about why that clock so often feels wrong. It is about the disconnect between the time that governs the universe and the time that governs us. This strange, elastic feeling is not an error in our perception. It is a clue. A trail leading toward one of the deepest mysteries of physics, biology, and consciousness itself. Today, we will follow that trail. Slowly, we will journey from the edge of the cosmos to the inner workings of the mind, to ask a simple, yet profound question. What is time, really? Welcome. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a quiet room, a busy city, or somewhere in between, feel free to share where you're watching or listening from. 2 clocks, 1 reality. At the heart of our confusion lies a tale of 2 clocks. The first is the time of physics. It is on the wall, on the wrist, on the phone. It is relentless and predictable. Each second is precisely as long as the last, defined with atomic precision. This is objective time, the consistent measure that schedules trains and launches rockets. It ticks onward, utterly indifferent to whether you are bored or ecstatic. The ancient Greeks called this chronos. But then, there is the second clock. This clock is inside you. It has no gears or batteries. It is built from memory, emotion, and attention. This is subjective time, the internal sense of time shaped by experience. It is a wild, unpredictable timekeeper. It can stretch a second into a miniature lifetime or compress a decade into a fleeting thought. The Greeks had another word for this: kairos, the opportune, qualitative moment. We exist in the tension between these two. The unfeeling, universal beat of chronos and the deeply personal, fluctuating rhythm of kairos. This raises a central question. Why does the time on the wall feel so different from the time in our minds? To begin the search for an answer, we must first turn our attention outward, to the great, unfeeling clock of the cosmos. What we find is that even the simple clock on the wall is anything but the old clockmaker, Newton's dream. For much of human history, our understanding of time was simple and intuitive. This view was best articulated by Sir Isaac Newton. For him, time was absolute. He envisioned it as a great, cosmic river, flowing equably without regard to anything external. In Newton's universe, time was a single, monolithic entity, the ultimate backdrop for reality. A second on Earth was the same as a second on Jupiter. It did not speed up or slow down, it just was. This is the time of our common sense. It is a clean, tidy, clockwork universe. For building bridges, baking cakes, and catching a bus, Newton's absolute time works perfectly. For over 200 years, this was the undisputed picture of time. It was elegant, it was simple, and it was not correct. The clockbreaker, Einstein's revolution. The man who broke Newton's universal clock was a 26-year-old patent clerk in Bern, Switzerland. In 1905, Albert Einstein published his theory of special relativity, and with it, shattered our conception of time. His insight began with a puzzle. The speed of light in a vacuum, physicists had discovered, was constant. It is always the same, no matter how fast you move toward or away from it. This is unlike anything else. If speed is distance divided by time, and the speed of light cannot change, then something else in that equation must be flexible. His radical conclusion was that time itself must be relative. This led to one of the most mind-bending consequences in all of science: time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. This is not a trick of perception. In the famous twin paradox, a twin who travels near the speed of light and returns to Earth will be physically younger than the sibling who stayed behind. Her clock, her biology, her every heartbeat, literally experienced fewer moments. 10 years later, Einstein's theory of general relativity added another layer of weirdness. Gravity also warps time. Time moves slower in stronger gravitational fields. A clock at sea level ticks ever so slightly slower than a clock on Mount Everest. This is not a theoretical curiosity. It is a practical reality. The GPS that guides our phones relies on a network of satellites moving very fast in a weaker gravitational field. If Einstein's equations were not used to constantly correct for this time difference, the entire system would fail within minutes. The next time you use a map on your phone, you are relying on the understanding that time is not a constant river, but a flexible, bendable fabric. The fabric of reality, spacetime. So, if time is not a universal clock, what is it? Einstein's theories led to a revelation articulated by his former professor, Hermann Minkowski. Space and time are not separate. They are woven together into a single, four-dimensional continuum, spacetime. Minkowski famously declared, "Henceforth, space by itself, and time by itself, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." The best way to visualize this is to imagine space-time as a giant, flexible sheet. Massive objects create curves in this fabric. What we perceive as gravity is simply as following the straightest possible path along these curves. But it's not just space that curves. Time does too. The deeper the gravitational well, the slower time flows. Near a black hole, an observer watching from a safe distance would see a clock falling toward it tick slower and slower, appearing to freeze at the event horizon. For the clock itself, time would continue to pass, but its now would be wildly different from the now of the distant observer. This leads to one of the most challenging ideas in physics, the block universe. If past, present, and future are simply directions in this four-dimensional spacetime, it could imply that all of time, every moment that has been and ever will be, already exists simultaneously. Our consciousness is like a light illuminating a single slice of a loaf of bread, moving from past to future. But according to this model, the entire loaf is already there. This is a deeply unsettling idea. It seems to rob us of free will and makes the flow of time an illusion. And it raises an obvious question. If the past and future are just as real as the present, what gives time its direction? The arrow of time. Why yesterday is gone forever. We all experience time as a one-way street. A broken glass does not reassemble itself. We grow older, not younger. This relentless forward march is what physicists call the arrow of time. The fundamental laws of physics would work just as well running backward as they do forward. So where does this powerful, unidirectional arrow come from? The most widely accepted answer comes from thermodynamics and a concept known as entropy. Entropy is, in simple terms, a measure of disorder. The second law of thermodynamics states that in an isolated system, total entropy will always tend to increase. The universe seems to follow this rule. It is believed to have begun in an incredibly ordered, low-entropy state at the Big Bang. Ever since, it has been expanding, cooling, and becoming more disordered. This continuous increase in cosmic disorder is what gives time its direction. The past is the direction of low entropy, the future is the direction of high entropy. We can remember the past because it was a more ordered state. We cannot remember the future because it is a sea of high entropy possibilities. So physics presents us with this grand, yet paradoxical picture. And yet, this still doesn't explain it. It doesn't explain why a minute waiting for a text message feels longer than an hour with a loved one. To understand that, we have to turn our gaze away from the cosmos and look inward. The feeling clock, time in the eyes of the mind. Physics gives us a time that is flexible, but it does not account for feeling. For that, we need to turn to our own consciousness, to the process scientists call chronoception, the brain's subjective sense of time. The brain does not have a single, dedicated organ for time. There is no time nerve. Instead, time perception is a construction, a story the brain tells itself by weaving together information from many different areas. It involves parts of the brain related to attention, memory, and emotion. This is why our internal clock is so easily swayed. It's not a precise instrument, it's a creative artist. The scribe of time, the role of memory. One of the most powerful factors shaping our sense of time is memory. Our judgment of a past duration is heavily influenced by the number of new memories we formed. Think about a vacation to a new city. While you are there, the days might feel like they are flying by. But looking back, that 1 week can feel as long and rich as a month of normal routine. Why? Because everything was novel. Your brain was working overtime, encoding countless new experiences. The sheer density of these memories gives the period its retrospective length. Now, contrast this with a typical week at work. The commute, the tasks, the lunch are all familiar. You are running on autopilot. Your brain does not need to create detailed new memories. When Friday arrives, the week seems to have vanished. There are fewer distinct, mental files to mark its passage. This same principle offers a compelling explanation for why time seems to speed up as we get older. A child's life is an endless cascade of firsts. Almost everything is a novel experience. As we age, life inevitably becomes more routine. We form fewer novel memories, so when we look back, the mental data is less dense. This creates the illusion that time is accelerating. Proportionality also matters. For a 5-year-old, 1 year is 20% of their entire life. For a 50-year-old, it is just 2%. The focus of time, the role of attention. While memory shapes our perception of the past, attention governs our experience of the present. Attention is a finite resource. How you allocate it has a dramatic effect on your internal clock. When you are deeply absorbed in an activity, a state of flow, your attention is fully dedicated to the task. You are not allocating any mental resources to monitoring the passage of time, so it seems to vanish. The part of your brain that would normally be checking the clock is busy. The opposite happens when you are bored. There is nothing to engage your attention, so your brain turns its focus inward and begins to monitor time itself. You become hyper-aware of every second ticking by. With your attention focused squarely on the clock, time seems to slow to a crawl. Essentially, your brain makes a trade-off. When an experience is rich, the brain prioritizes processing it over tracking duration. When an experience is dull, it has plenty of spare capacity to watch the clock. The emotion of time, the role of feeling. Perhaps the most potent force that can warp our internal clock is emotion, likely as a survival mechanism. The classic example is fear. Many people in life-threatening situations report a slow motion effect. The event seems to unfold frame by frame. This is because the amygdala, the brain's fear center, goes into overdrive. It commands the rest of the brain to absorb as much sensory information as possible. When the memory is played back, this high density of information makes the event seem to have lasted much longer. Your brain didn't slow down time, it just took a very high-speed recording of the moment. This response is so fundamental that recent studies suggest our very heart rate, quickening in fear or steadying in calm, can act as a biological pacemaker, helping to modulate the speed of our internal clock. Other emotions have powerful effects. Awe has been shown to make people feel like they have more time available, expanding the sense of the present. Conversely, joy often makes time fly, while sadness can make it feel like it's dragging. Our emotional state acts like a filter, coloring and shaping our perception of time. The synthesis, weaving two times together. Here we are, at the end of two paths. One led through physics, revealing a time that is relative and pushed forward by entropy. The other led into the mind, showing a time that is a subjective construction. This reveals not a conflict, but a partnership. Two descriptions of a single reality, one from the outside, and one from within. The time of physics is the fundamental framework. It is the riverbed, carved out by the laws of the universe. It sets the absolute constraints. An hour will never objectively last for two. This is the shared reality we all exist within. But subjective time is the water that flows through that riverbed. It is how we, as conscious beings, experience the journey. The riverbed may be fixed, but the water can flow quickly or slowly. Our perception is the experience of that flow. The job of the human brain is not to be a perfect atomic clock. Its primary job is to create a useful model of the world. A perception of time that stretches during danger, that flies by during moments of connection, and that feels long in retrospect for novel experiences is an incredibly adaptive tool. It's a clock built for living, not just for measuring. A new perspective on now. Understanding this duality doesn't grant us the power to stop time, but it can change our relationship with it. It allows us to see time not as a tyrant, but as a fascinating part of our own nature. When time feels like it's speeding up, we can recognize it as a sign that life has fallen into routine. It can become a call to action. The solution is not to wish for more time, but to fill the time we have with more life. To seek out novelty, break routines, and consciously create the dense memories that give our past its weight. To make our lives feel longer, not by adding years, but by adding firsts. And when time feels like it's dragging, it can become an opportunity. A moment of slowness is a chance for mindfulness, an invitation to pay attention to the details of the present we usually rush past. The physicist John Wheeler once said, "Time is nature's way of keeping everything from happening at once." Physics shows us how that works on a cosmic scale. But on a personal scale, our minds do the opposite. They take all the things happening at once and string them together into the coherent story we call a life. Ultimately, the richness of our existence is not measured by the objective ticks of a clock. It is measured by the subjective depth of our experiences. Time is both the unyielding canvas of the universe and the personal paint we use to create our story. The clock on the wall tells you what time it is. But only you can decide what to do with your time. If you enjoyed this slow journey into the nature of time, consider subscribing for more deep dives into the big questions that shape our understanding of the universe and ourselves. And we'd love to read your own experiences in the comments below. Tell us about a moment when time felt completely unreal for you. Why you can't unbreak an egg. It is a simple, almost silent event that happens every day, in kitchens all over the world. A gentle tap, a quiet crack, and the contents of a smooth, ordered shell spill out into a pan. It becomes breakfast. It is the beginning of a cake. It feels trivial, but the reverse never happens. No one has ever watched a cooked egg leap back from a pan, the white and yolk entangling themselves into their perfect, separated forms, before sealing themselves inside a pristine, unbroken shell. We all know this is impossible. We rarely even question it. It feels like a rule as fundamental as gravity, yet its origins are somehow stranger. What invisible law of nature prevents the pieces from flying back together? The reason is not just common sense. It is one of the deepest and most unbreakable principles in all of physics. It is the story of the arrow of time, and its quiet, forward march governs everything from a cooling cup of coffee to the ultimate fate of the entire cosmos. And it all begins with one simple, irreversible act. The one-way street. This isn't just about eggs. If you look closely at the world, you will see this one-way rule written into the fabric of almost everything. Milk poured into coffee swirls into a uniform, cloudy brown. It will never spontaneously separate itself back into a clean, white dollop. We remember what we ate for dinner yesterday, but we have no memory of what we will eat for dinner tomorrow. We are born, we live, and we age. Never the reverse. Each of these experiences points to the same conclusion: time has a direction. It seems to flow, much like a river, from a place we call the past, through the present moment, and into a territory we call the future. This directionality, this forward momentum, is what physicists refer to as the arrow of time. It feels intuitive, perhaps even obvious. But the moment you stop to ask, why, you encounter one of the most profound mysteries in science. Because when we peer into the fundamental laws that govern our universe, the laws that dictate the dance of atoms and the motion of galaxies, that arrow disappears. The river vanishes, and we are left with a still, silent lake, where forward and backward are indistinguishable. This is the central mystery. If the universe, at its most fundamental level, has no preferred direction of time, why does our reality seem to be trapped on a one-way street? The answer lies not in a force, but in a principle of chaos and probability. It is called the second law of thermodynamics. And to understand it, it is helpful to forget about eggs for a moment, and instead, think about a simple box of marbles. The physicist's puzzle. Before we consider that box, it is important to understand just how deep this puzzle runs. If a physicist were watching a video of two particles colliding, say, two electrons, they would fly toward each other, bounce off, and fly away. If that video were played in reverse, the two electrons would fly back toward the point of collision, interact, and retrace their original paths perfectly. Here is the stunning part. The physicist would have no way of knowing the video was being played in reverse. The laws of physics that govern that collision, electromagnetism, motion, gravity, they work identically whether time is running forward or backward. There is nothing in the core equations that describe reality at its most granular level that contains a play button. Physicists call this time reversal symmetry. This scales up. A video of our solar system shows planets tracing elegant ellipses around the sun. If reversed, they would simply trace the exact same ellipses in the opposite direction. According to the laws of gravity laid down by Newton and refined by Einstein, this is a perfectly valid physical scenario. There is no cosmic signpost that says, time this way. And yet, our world is full of those signposts. Every shattered glass, every cooling cup of tea, every memory formed. These are all processes that seem to declare, time flows this way, and only this way. This is the great contradiction that baffled scientists for more than a century. Our macroscopic world clearly has a powerful arrow of time, but the microscopic world of fundamental laws is completely ambivalent. It is as if the universe is built from bricks that have no concept of up or down, yet the entire building somehow points resolutely toward the sky. So where does this arrow come from? If it's not written into the fundamental rules, how does it emerge so powerfully on the grand scale of our reality? The solution comes not from a new force, but from understanding the overwhelming power of statistics and probability. It comes from understanding the single most important concept in all of thermodynamics, entropy. The secret ruler of the universe. Let's return to our box of marbles. Imagine a large, clear box with a thin divider down the middle. On the left, we place 1 million red marbles. On the right, 1 million blue marbles. The system is in a state of perfect order. All red on one side, all blue on the other. This is a very specific, highly structured arrangement, which physicists would describe as having low entropy. Entropy is, in simple terms, a measure of disorder or randomness. A highly ordered state is a low entropy state. Now, we lift the divider and gently shake the box. The marbles will begin to mix. A few blue will cross into the red territory, and a few red will cross to the blue. With more shaking, the mixing becomes more thorough, until we have a chaotic, purplish field of interspersed marbles. This messy, mixed-up state is a high-entropy state. It is disordered. Here is the crucial question. If you continue shaking that box for an hour, a day, or a billion years, what are the chances that all 1 million red marbles will spontaneously find their way back to the left side, and all 1 million blue marbles back to the right, recreating that perfect, initial state? The chances are so infinitesimally, mind-bogglingly close to zero that it is, for all practical purposes, impossible. But why? There is no force pushing the marbles to be mixed. No disorder field permeates the box. The reason is pure, simple probability. There is exactly one way for the marbles to be arranged in that perfect, low-entropy state. All red on the left, all blue on the right. Just one configuration. But how many ways are there for the marbles to be in a mixed-up, high-entropy state? The number is staggeringly, unimaginably vast. For any given marble, its position doesn't matter, and its neighbors could be red or blue. The number of possible configurations that look messy is astronomically larger than the single configuration that looks ordered. The universe doesn't have a preference for chaos. It simply tends to fall into the configuration that has the most possible ways of existing. A messy room has more available configurations than a tidy one. A shuffled deck of cards has more configurations than one sorted by suit and number. This is the second law of thermodynamics. The total entropy, or disorder, of an isolated system will almost never decrease over time. It can only stay the same or, far more likely, increase. Things get messy not because of some mystical force, but because there are infinitely more ways to be messy than to be tidy. The universe is just playing the odds. And this simple statistical rule is the source of time's arrow. Time moves forward because forward is the direction of increasing entropy. It is the path from a single, unlikely ordered state to one of the countless, likely disordered states. Shaking the box is the arrow of time for the marbles. And breaking an egg is the arrow of time for your breakfast. The unscrambling of the egg. Now we can return to the kitchen counter. An unbroken egg is a marvel of low-entropy biological engineering. Its shell is a specific, ordered structure of calcium carbonate crystals. Its shape gives it remarkable strength against static compression, though recent studies suggest its resilience to impact is actually greatest when it lies on its side, where it can bend to absorb energy. Inside, its proteins and fats are arranged in a very particular way, the yolk separate from the white. Like our marbles, this configuration is a highly specific, ordered state. Then comes the crack. The contents spill out. Whisked and heated, the long chains of proteins unfold and tangle, forming a solid, opaque mass. The yolk and white are now irrevocably mixed. The molecules are no longer in their neat compartments. They are in a chaotic, scrambled, disordered mess. This is a high-entropy state. Just as with the marbles, the reason an egg cannot unbreak is probability. For it to unscramble, trillions of tangled protein and fat molecules would have to, by random chance, move in exactly the right way to untangle. Heat would have to flow back out of the cooked egg and perfectly refold the proteins. The shattered pieces of the shell would have to leap up, align themselves perfectly, and refuse their chemical bonds. Is it physically possible? In a purely technical sense, the laws of motion for each atom are time reversible, so yes. But is it statistically probable? Absolutely not. The number of molecular arrangements we call a scrambled egg is astronomically larger than the single arrangement we call a whole egg. The universe, in moving from whole to scrambled, is simply moving from an incredibly unlikely state to an overwhelmingly likely one. It is following the arrow of entropy. This same principle explains why a cup of hot coffee cools down. The fast-moving, energetic molecules are concentrated in the cup, a low-entropy state. Over time, they transfer their energy to the slower molecules in the surrounding air. The energy spreads out, becoming more disordered. Entropy increases. You will never see a lukewarm cup spontaneously draw heat from the room to become hot, for the same reason an egg will not unscramble itself. It even explains why we remember the past and not the future. Forming a memory is a physical process where neurons form new, ordered connections. This process requires energy, and by burning that energy, our bodies release heat into the environment, increasing the total entropy of the universe. A memory is an ordered record of a past event, viewed from the present moment of higher entropy. In a way, memory is the wake left behind as we move along this current of increasing entropy. We can't remember the future because, from our perspective, its entropy has not yet been generated. Everyday life is a quiet demonstration of the second law. A building crumbles. A sandcastle is washed away. An ice sculpture melts into a puddle. All are journeys from order to disorder. But this raises a larger question. If the universe is on a one-way trip to messiness, that must imply it started out incredibly tidy. The cosmic egg. If you walk into a room and find a deck of cards perfectly arranged by suit and number, you know that someone must have put in the effort to arrange it. A state of low entropy implies an even lower entropy state in its past. Our universe is full of incredible order. There are galaxies, stars, and planets. There is life. These are all pockets of immense structure. Our sun is a highly ordered ball of gas, not a random cloud diffused through space. You are a breathtakingly complex collection of trillions of cells working in concert. These are all states of relatively low entropy. If the second law is true, and everything is constantly becoming more disordered, this presents a colossal paradox. How did all this order arise in the first place? If you trace the arrow of time backward, from scrambled egg to whole egg, from cold coffee to hot coffee, you are moving toward states of lower and lower entropy. This logic, when traced all the way back for 13.8 billion years, leads to a staggering conclusion. The universe must have begun in a state of almost unimaginable order. A state of prodigiously low entropy. This was the Big Bang. We often picture the Big Bang as a chaotic explosion. From a thermodynamic perspective, it was the opposite. The entire observable universe was compressed into a space smaller than an atom, in a state of incredible heat, density, and uniformity. This uniformity was its order. It was a perfect, cosmic egg. This initial, low-entropy state is the ultimate source of the arrow of time. It is the wound-up clock that has been ticking down ever since. The history of the cosmos is the story of the universe unfolding from that one, special, highly unlikely state into a multitude of more probable, more disordered states. The formation of a star might seem like an increase in order, and locally, it is. Gravity pulls diffuse gas into a dense, ordered structure. But this process is incredibly inefficient. As the star ignites, it radiates a tremendous amount of heat and light out into the void of space. The small decrease in entropy from forming the star is dwarfed by the colossal increase in entropy from all the energy it blasts into the cosmos. Life is the same. You maintain your biological order by consuming ordered energy, like food, and converting it into disordered energy, like heat. You are a temporary island of order, purchased at the cost of a much larger increase in the total disorder of the universe. So, each time you break an egg, you are participating in a cosmic process. You are witnessing a tiny fulfillment of a law whose origin is written into the very first moment of the universe. The arrow of time in your kitchen began at the dawn of time itself. The great cosmic fade out. If the story of the universe is a one-way journey from order to disorder, then where is it going? The second law of thermodynamics doesn't just explain the past, it predicts the future. And it is a future of profound stillness. As the universe continues to expand, entropy will continue to increase. On the grandest of scales, this process plays out over eons. Stars will exhaust their fuel and fade to black. The universe will become dark, populated by stellar remnants, white dwarfs, neutron stars, and black holes. Over truly unimaginable timescales, even these objects will decay. Protons themselves may dissolve into a sea of low-energy particles. The last holdouts of structure will be black holes. But as Stephen Hawking discovered, black holes themselves radiate energy. Slowly, painstakingly, they evaporate. The largest will take a Google years, a 1 with 100 zeros, to disappear, but eventually, they too will be gone. At this point, the universe will have reached a state of maximum entropy. Physicists call this the heat death. It will be a vast, cold, dark, and perfectly uniform cosmos. The energy once concentrated in the Big Bang will be spread so thinly that nothing can happen. There will be no temperature differences to drive any process. The universe will be a featureless soup of particles, drifting through an endless, cold night. In this final state, the arrow of time loses its meaning. The arrow is defined by the increase of entropy. If entropy is at its maximum and can increase no further, the arrow vanishes. The river of time will have emptied into a boundless, static ocean. The same law of probability that prevents your egg from unscrambling itself dictates that the cosmos will eventually scramble itself into a final state of complete disorder, from which it can never return. This journey, from a simple kitchen observation to the beginning of time and its ultimate end, is at the core of what we explore here. It is the process of taking the world you think you know and revealing the deeper, stranger reality hiding just beneath the surface. If this kind of calm exploration into the laws of the universe helps you unwind, consider liking the video and subscribing to the channel. And feel free to share in the comments a small, everyday example of this one-way street that you've noticed in the world around you. The meaning of the arrow. So what does this mean for us, living our brief lives in the middle of this grand cosmic story? It is a sobering thought that our universe is governed by a law of universal decay. And yet, here we are. Life represents a quiet rebellion against entropy. It is a process that temporarily and locally defies the universe's slide into chaos. A single seed, harnessing ordered energy from the sun, organizes soil and air into the magnificent, low-entropy structure of a tree. We are eddies of order in the relentless river of entropy. We are pockets of breathtaking complexity in a cosmos that trends towards simplicity. This rebellion, however, comes at a cost. Life builds its small sandcastles of order only by using ordered energy and expelling disordered waste, thereby increasing the total entropy of the universe. We are not breaking the second law. We are exploiting it, creating tiny, intricate pockets of order while dutifully increasing the overall chaos of the cosmos. This perspective recasts our existence. Our consciousness and our ability to create are products of this temporary victory of order over chaos. The very feeling of moments flowing one into the next is our minds processing reality along the only direction available, the direction of increasing entropy. There is something both melancholy and beautiful in this. It means that purpose, structure, and meaning are not the default state of the universe. They are rare and fleeting. They are things that must be built and maintained against the overwhelming tide of probability. Every act of creation, whether it is an artist painting a canvas or an engineer building a bridge, is a small act of defiance. It is a temporary victory against the all-encompassing law of cosmic decay. The arrow of time is not a cruel master, but a canvas. It provides the directionality that makes stories possible. The fact that eggs break and don't unbreak is the same reason we can learn from our mistakes, and the same reason we can grow. It is the law that makes life's journey a one-way trip, and therefore, makes every moment precious. So, why can't you unbreak an egg? We started with a simple question, and the answer has taken us to the edge of existence and back. An egg cannot be unbroken for the same reason a cup of coffee gets cold, and for the same reason the universe itself will one day fade into a cold, silent emptiness. An egg cannot be unbroken because the universe is on a one-way trip, governed by the simple and elegant logic of probability. There are more ways to be broken than to be whole. More ways to be messy than to be tidy. The universe is not forcing things to break down. It is simply falling into its most natural, most probable state. And we call this falling, time. Each time an egg is cracked, it is a small participation in a process that began 13.8 billion years ago. It is a quiet echo of the Big Bang, following the same unbreakable law that dictates the fate of the cosmos. The arrow of time isn't just something we experience. It is the unfolding story of the universe, from a single, ordered beginning, toward a vast, silent end. How a stick in the dirt became the first clock. Before there were minutes and seconds, before clocks and phones, humanity lived in a world without defined time. Life was a fluid, unbroken stream of daylight and darkness, governed only by the rising and setting of the sun, the pangs of hunger, and the chill of the night. There was no way to schedule a hunt, to coordinate the planting of crops, or to organize the building of a shelter. It was a world of instinct, a great blur of moments without names. But deep within the human mind, a new kind of consciousness was stirring. It was the recognition of patterns, the understanding that the universe was not just a series of random events, but a grand, repeating cycle. This quiet realization, that the world was a clock just waiting to be read, would change everything. This is the story of how a humble stick in the dirt became the first clock, and how it laid the foundation for the world we know today. If this kind of calm exploration into our shared past helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The world before ours. For our earliest ancestors, tens of thousands of years ago, the concept of a day, as we know it, did not exist. There was no Monday, no 9 to 5, no, I'll see you at noon. Life was an unbroken cycle of sunrise, daylight, sunset, and the deep, often dangerous, black of night. Survival was dictated not by a schedule, but by immediate cues from the natural world. The sun's warmth on the skin dictated when to be active. The behavior of prey dictated the rhythm of the hunt. The feeling of hunger was the most personal clock of all. Time was not an external force to be measured. It was an internal, subjective experience. It was felt, not counted. For a hunter-gatherer, time might have been measured in the effort it took to track a deer, or the number of berries that could be gathered before dusk. The workday was simply the period between sunrise and sunset, a block of opportunity that expanded in the summer and shrank in the winter. But humans are, above all, pattern-seeking animals. Staring at the sky, generation after generation, our ancestors began to notice the undeniable regularities. The sun always rose in one direction and set in another. The moon grew from a sliver to an orb and back again with predictable grace. This was the critical cognitive leap. The moment a mind shifted from simply reacting to the sun to understanding its position as a form of information. The realization that the sun's path could be used to predict future events was the true birth of timekeeping. Before they could divide the day, early humans did mark longer passages of time. Archaeologists have found ancient bones, some perhaps 20,000 years old, with notches that seem to correspond with the phases of the moon. This was a way to track the passage of months, likely crucial for anticipating seasons. But it did nothing to solve the immediate problem. How do you divide a single period of daylight? The need for a daily clock was becoming urgent, setting the stage for an invention of unparalleled simplicity. The genius of the moving shadow. The solution, when it came, was born from a moment of quiet observation. Perhaps it was a spear planted in the soft earth during a rest, or just a stick pushed into the ground. As moments passed, its shadow moved. It crept across the ground, a silent, steady pointer driven by the unseen engine of the cosmos. In that observation, the idea of the world's first clock was born. This simple vertical stick, a gnomon, operates with an elegant simplicity. In the morning, it casts a long shadow to the west. As the sun climbs, the shadow shrinks, becoming shortest at midday. This moment of the shortest shadow is a crucial, fixed point. After this, as the sun descends, the shadow lengthens again, now stretching eastward until it dissolves into twilight. While the idea itself is ancient and lost to prehistory, the first physical evidence of this practice appears much later, but the principle remains timeless. Suddenly, the great blur of daylight had a structure. It had a definitive halfway point. The day could be split into two parts: the morning, before the shortest shadow, and the afternoon, after the shortest shadow. This simple division was revolutionary. A hunting party could agree: we will hunt until the shadow is at its shortest, and then we will rest. This was the birth of the appointment, the schedule, the deadline. The next logical step was to mark the ground. By placing stones or drawing lines at the tip of the shadow's path, our ancestors could create the first sundial face. A circle of stones around the gnomon could become a public, standardized timepiece for an entire community. Now, meet at the third stone was a precise and understood instruction. This wasn't just about convenience. It was about social organization, allowing for the kind of collective action that is the hallmark of human civilization. From stick to stone. As societies grew, the need for a more permanent, public form of timekeeping arose. The idea of the gnomon needed to be scaled up, transformed from a personal tool into a civic institution. No civilization did this with more grandeur than the ancient Egyptians. Around 3500 BC, the Egyptians began erecting obelisks. These towering, four-sided monoliths of stone were primarily religious and memorial monuments dedicated to the sun god Ra. But their massive shadows, sweeping across marked plazas, also served as a clock for the entire populace, dictating the rhythms of life for laborers, merchants, and priests. Timekeeping was inseparable from the spiritual world. The shadow's journey was a reflection of Ra's journey across the sky. The Egyptians were among the first to formally divide daylight into 12 parts. This is a precursor to our 12-hour clock face, but with a fascinating difference. Their hours were temporal, meaning they were not of a constant length. An hour was simply 1/12 of the total daylight. In the long days of summer, an hour might have been 75 of our modern minutes. In the short days of winter, it could shrink to just 45. This system might seem strange to us, but it was perfectly logical for a society whose life was tied to the sun. Around 1500 BC, the Egyptians also developed smaller, more personal timepieces. One was a clever L-shaped shadow clock, with a crossbar that cast a shadow onto a marked ruler. It had to be oriented east in the morning and then turned to face west in the afternoon, allowing officials to measure work hours with greater precision. It was the ancient equivalent of a supervisor's watch, a tool for managing the newly quantified resource of human labor. The problem of a sunless sky. Shadow clocks, from the simple gnomon to the mighty obelisk, were a triumph. But they had a fundamental limitation, one that became apparent every single evening. What happens when the sun goes down? And what do you do on a day when the sky is thick with clouds? At night, societies were plunged back into the great blur. The need for timekeeping was just as critical for military guards, temple priests, and physicians. Ancient astronomers, particularly in Egypt, devised a clever but complex workaround using the stars. They tracked groups of stars called decans as they rose on the horizon at regular intervals, serving as a kind of celestial clock face. This method was sophisticated, but it required a crystal-clear night and the expert knowledge of a trained astronomer priest. It was not a tool the average person could use. The problem was clear. Timekeeping needed to be liberated from the sky. Humanity needed an invention that could measure time on its own terms, indoors, day or night, in any weather. The solution would come not from the sky, but from the element of water. Capturing time in a jar. With the sun and stars proving to be fickle, ancient inventors turned to one of the most fundamental forces of nature, gravity. The solution was the asterisk clepsydra, a Greek name that poetically translates to water thief. This was the water clock, an invention so profound it would remain the most accurate timekeeping device in the world for nearly 3,000 years. The basic concept is beautifully simple. A container filled with water has a small hole near the bottom. As water drips out, the water level inside drops. By marking a scale on the inside, you can measure the passage of time. The earliest known example was found in the tomb of the pharaoh Amenhotep I, dating to around 1500 BC. It was humanity's first successful attempt to create an artificial and continuous measurement of time. However, these early clocks had a physics problem. Due to water pressure, the flow is faster when the vessel is full and slows as it empties. The Egyptians came up with a brilliant solution. Instead of straight-sided pots, they crafted stone vessels with downward sloping sides, calculating the precise conical shape needed to ensure the water level dropped at a much more uniform rate. It was an astonishingly advanced application of fluid dynamics. Later, the Greeks and Romans took the technology to an even higher level. The brilliant inventor Ctesibius of Alexandria, in the 3rd century BC, revolutionized the clepsydra. He designed systems where a float would rise with inflowing water. Attached to this float was a pointer that indicated the hour on a marked column. He even connected the rising float to gears that could trigger whistles or gongs. He had, in effect, invented the world's first alarm clock. The water clock freed timekeeping from weather and daylight. It became portable and private, used in Roman law courts to time speeches and by the military to regulate guard shifts. The grand cosmic clocks. While the sundial and water clock divided the day, our ancestors were simultaneously reading two much larger clocks, the moon and the seasons. These grand cosmic cycles were the first calendars, providing the framework for agriculture, religion, and long-term planning. The moon was humanity's first month. Its predictable 29.5-day cycle of phases was easy to track. It was the Babylonians who truly mastered the lunar calendar, but they gave us something even more profound. They used a base 60 mathematical system. From them, we directly inherited our 60-second minute and our 60-minute hour. Every time you look at a clock, you're seeing a direct legacy of Mesopotamian mathematics from 4,000 years ago. Zooming out even further, the grandest clock of all was the yearly cycle of the seasons. Understanding this annual rhythm was a matter of life and death. To track it, ancient peoples built monumental observatories. The most famous is Stonehenge in England. It is not a random collection of stones, it is a precisely engineered solar calendar. On the summer solstice, the rising sun aligns perfectly with the monument's central axis. Relevant knowledge. These alignments were critical announcements to the community that the Earth had reached a turning point in its annual journey. From the Egyptian calendar based on the star Sirius to the complex interlocking calendars of the Maya, cultures across the world learned to read these epic cycles. The echo of a shadow. The journey from a simple stick to the elaborate water clocks of the ancient world was a monumental saga. Each invention was a response to the limitations of the last, a relentless drive for greater precision. The next great leap would be the mechanical clock in the Middle Ages, but that is a story for another time. What is truly profound is how these foundational ideas are still with us, embedded so deeply in our culture that we rarely notice them. Our day is divided into 24 hours, a concept descended from the Egyptians dividing daylight and night into 12 parts each. Our hour is divided into 60 minutes, a legacy from Babylonian scribes. Relevant knowledge. The very act of scheduling a meeting or setting an alarm is the end result of a chain of innovation that began with an anonymous ancestor noticing a shadow moving across the ground. That first clock wasn't just about telling time. It was about creating order from chaos. It was a tool that enabled the complex coordination required to build farms, cities, and empires. Every tick of a modern clock is an echo of that ancient past. It's an echo of a priest watching a shadow creep towards a marker, a philosopher timing a speech with dripping water, and a farmer watching the solstice sun rise between two standing stones. Our hyper-scheduled world is built on a foundation of shadow and stone, a testament to the timeless human quest to understand and master the world around us. And now, we want to hear from you. Let us know in the comments. If you were transported back in time with all your modern knowledge, but no tools, how would you start telling time? What would be your first invention, and how would you build it? Remember that even in our fast-paced world, the ancient rhythms of the sun, moon, and stars are still there, ticking away just as they always have. Your body is a time machine. For a long time, we have thought of time as something simple. A steady rhythm, marching forward second by second, the same for everyone, everywhere. But deep within the rules of the universe lies a different story. One where time is not a constant, but a fabric, capable of being stretched and bent. And the most surprising part of this story is that we are a part of it. Your own body, in its quiet, biological functions, is constantly interacting with this fabric, subtly altering its own journey into the future. It sounds like something imagined rather than evolved, a concept from a world that no longer exists. And yet, it is a fundamental part of our reality. Every time you walk to the store, every time you climb a flight of stairs, every movement you make is a small, real adjustment to your personal rate of travel through time. This isn't a story of fiction. This is a journey into the quiet physics that shows how your own body can function as a time machine, and how you age just a little bit slower than someone standing still. The one simple rule. To understand this, you do not need to be a physicist. You only need to accept one simple, and quietly strange, fact about the way the universe is built. A single rule that sits at the foundation of Albert Einstein's work on relativity. That one rule is this: the speed of light is the same for everyone. At first, this might seem straightforward. But what it implies changes our sense of reality entirely. Imagine standing on a road as a car passes at 50 miles per hour. From your perspective, it moves at that speed. If you were in another car moving in the same direction at 30 miles per hour, the first car would only seem to pull away at 20 miles per hour. This is how we experience the world. Speeds are relative, but light does not follow these rules. Imagine you are in a spaceship, moving at an incredible speed, half the speed of light. You turn on a light, and the beam shoots forward. To someone watching from a distant planet, intuition suggests the light's speed should be your speed plus the light's speed. But that is not what happens. The observer on the planet will measure your light beam moving at exactly the speed of light, which we call c. And you, inside your ship, will also measure that same beam moving away from you at exactly c. It does not matter how fast you are moving, or in what direction. Every single observer will always measure the speed of light in a vacuum to be the exact same number. This is not a theory, it is one of the most rigorously tested facts in science. It is the universe's ultimate speed limit. And this one stubborn fact is the key. Because if the speed of light must be the same for everyone, then something else has to be flexible. That something else is time itself. The light clock. To see how this works, we can use a thought experiment. It is perhaps the most important tool for understanding this idea, the light clock. Imagine a simple clock made of two mirrors, with a single particle of light, a photon, bouncing between them. Each time the photon travels from the bottom mirror, hits the top, and returns, we count one tick. First, let's picture this clock sitting still next to you. You watch the photon travel straight up and then straight down. The distance it travels for one tick is simply up and down. The time for that tick is this distance divided by the photon's speed, c. This is the proper time of the clock, the time measured by someone at rest with it. Now, let's put that same clock on a fast-moving train. You are standing on the station platform, watching it go by. From your perspective, the photon's journey looks different. In the time it takes the photon to travel from the bottom mirror to the top, the clock itself has moved forward. So, from your point of view, the photon travels on a diagonal path. Then, on its way back down, the clock moves again, and the photon follows another diagonal path to meet the bottom mirror. Its path is no longer straight up and down. It is now a zigzag. And a diagonal line is always longer than a straight one. From where you stand, the photon in the moving clock has to travel a longer distance for every tick. This is the critical moment. We must remember our unbreakable rule. The speed of light, c, is the same for all observers. You on the platform and a person on the train must both measure that photon's speed to be c. But from your perspective, the photon is traveling a longer distance. If speed is constant, but the distance is longer, it must mean the time for that journey is also longer. The duration of one tick on the moving clock, as you measure it, is longer than a tick on an identical clock sitting next to you. In other words, from your perspective, the moving clock is ticking slower. This is not an illusion or a mechanical flaw. Time itself for the moving clock is passing more slowly relative to yours. This is called time dilation. The faster something moves, the longer its light path becomes, and the slower its time flows. The grand reveal: you're the clock. So, moving clocks run slow. That is a fascinating piece of physics. But what does it have to do with your body? Here, the story connects back to us. You are a clock. Your body is an unbelievably complex biological machine. Every process that keeps you alive, from the firing of neurons in your brain to the beating of your heart, is governed by fundamental physical laws. These are, at their core, a series of chemical reactions, which are themselves electromagnetic interactions between atoms. The speed of these interactions is limited by the same ultimate speed limit, the speed of light. The same constant, c, that governs the light clock also governs the speed limit of every biological process happening inside you. Therefore, if the passage of time is altered for a moving light clock, it must also be altered for a moving biological clock. Your body's internal, biological time is subject to the exact same laws. When you move, the rate of your biological processes, what we call aging, slows down relative to someone who is stationary. The laws of relativity do not distinguish between a clock made of mirrors and a clock made of cells. Physics is universal. If motion slows time, it slows all time, including the time your body experiences. The time machine payoff: running for the bus. Now we can return to our quiet, everyday example: running for a bus. When you are standing still at the bus stop, your biological clock ticks in unison with a person sitting on a bench next to you. The moment you start to run, you have changed your state of motion. For the person on the bench, your time has now slowed down. The electrochemical signals in your brain are traveling at a rate that is infinitesimally, but measurably, slower. Your heart is beating at a rate that is fractionally slower in their frame of reference. The very process of aging in your cells has been subtly retarded. Of course, at the speed of a running human, the effect is almost immeasurably small. We never notice it in our daily lives. But minuscule does not mean zero. The effect is real. In that moment of running, you are aging ever so slightly less than the person sitting on the bench. You are traveling into the future at a different rate. When you stop, you will have lived a fraction of a second less than them. Your body, through the simple act of motion, has functioned as a time machine. It has subtly altered your personal journey through the fourth dimension, quantifying the unseen, real-world proof. This may feel like a thought experiment, but there is real, tangible proof that this happens. Time dilation is a practical reality we have measured and now depend on. The first direct proof came in 1971 with the Haffel-Keating experiment. Two physicists flew four incredibly precise atomic clocks on commercial flights around the world. They left other synchronized clocks behind at the U.S. Naval Observatory. When the traveling clocks returned, they were no longer in sync with the stationary ones. The clocks that flew eastward, moving with the Earth's rotation, lost about 59 nanoseconds. The clocks that flew westward, against the rotation, gained about 273 nanoseconds. The results perfectly matched the predictions. Time had physically passed at different rates. Perhaps the most powerful and ongoing demonstration is the Global Positioning System, or GPS. Your phone works by receiving signals from satellites, each with an extremely precise atomic clock. These satellites are moving at about 14,000 kilometers per hour. Because of this speed, their clocks should tick slower than clocks on Earth by about 7 microseconds every day. And yet, there is another effect. Because they are far from Earth, they feel weaker gravity, which causes their clocks to tick faster by about 45 microseconds per day. When you combine these two effects, the net result is that the clocks on GPS satellites run faster than clocks on the ground by about 38 microseconds every day. If scientists didn't account for this, GPS navigation errors would accumulate at a rate of about 10 kilometers every day. The fact that your GPS can guide you to a quiet street corner is daily, irrefutable proof that time is relative. Nature provides its own beautiful experiment as well, in the form of particles called muons. Muons are created when cosmic rays strike the upper atmosphere and have a very short average lifetime of only 2.2 microseconds. Even traveling near the speed of light, they should only be able to travel about 660 meters before they decay. Yet, we detect vast numbers of them at the Earth's surface, after they have traveled many kilometers. This is possible because the muons are traveling so fast that their internal clocks slow down dramatically from our perspective, stretching their lifespan and giving them enough time to complete the long journey to the ground. The other half of the story, gravity's grip on time. So far, we have explored how motion affects time. But as we saw with the GPS satellites, that is only half the picture. Einstein's general theory of relativity revealed something even more profound. Gravity itself bends time. He described space and time as a single, four-dimensional fabric called spacetime. Massive objects, like planets, warp this fabric, like a bowling ball on a trampoline. This curvature is what we feel as gravity. And just as motion through this fabric affects time, the curvature of the fabric also affects time. The stronger the gravity, the slower time passes. This has been experimentally verified, and it leads to one of the most personal consequences of relativity. Your head is aging faster than your feet. Right now, your feet are closer to the center of the Earth than your head. They are in a slightly stronger gravitational field. The difference is infinitesimal, but it is real. Time is passing ever so slightly slower for your feet than it is for your head. Physicists have measured this effect, finding that a clock raised by just 33 centimeters runs slightly faster. Over a 79-year lifetime, a person's head will age approximately 90 billionths of a second more than their feet. It is a number so small it is difficult to imagine, but it confirms a fundamental truth. Time flows at different rates at different points in space. Near a black hole, where gravity is immense, this effect becomes extreme. To a distant observer, an astronaut falling toward a black hole would appear to slow down, eventually seeming to freeze in time as their clock ticks infinitely slowly. For the astronaut, time would feel normal, but centuries might pass for the outside universe. The twin paradox, a story of time travel. The ultimate story to illustrate this strange reality is the twin paradox. It brings everything we have discussed into a single, human narrative. Imagine two twins, Alice and Betty. Betty stays on Earth. Alice embarks on a journey in a spaceship, traveling to a distant star at 95% the speed of light. From Betty's perspective on Earth, Alice is the one in motion. She knows that because of her sister's immense speed, Alice's aging process is running much slower. The round trip, from Betty's point of view, takes 40 years. When the ship lands, Betty is 40 years older. But for Alice, time has passed much more slowly. At that speed, for every 3.2 years that passed for Betty, only 1 year passed for Alice. The 40-year trip felt like only about 12.5 years to her. When Alice steps out of the spaceship, she is still a young woman, while her twin sister is now 27.5 years her senior. Alice has effectively traveled into Earth's future. You might wonder, isn't motion relative? Shouldn't Alice see Betty's clock running slow? This is the paradox, and the solution lies in acceleration. Their experiences are not symmetrical. Betty stayed in one consistent frame of reference. Alice had to accelerate, decelerate, and turn around. It is this change in reference frames that breaks the symmetry and makes her the one who experiences less time. This isn't just a story. If we could build such a ship, the laws of physics demand this is what would happen. It is an incredible thing to consider. That the flow of time isn't a universal constant, but a personal experience. If this kind of calm exploration into the hidden world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a city, or somewhere quiet in between, feel free to share where you're watching from. The frontiers and mysteries. We have established that time is relative. But this discovery also opens the door to deeper mysteries. We see the effects of time, but what is it? Physicists talk about the arrow of time. Why does time seem to flow in only one direction? One leading idea is linked to entropy, a measure of disorder. The universe as a whole is moving from a state of low disorder, the Big Bang, to high disorder. This relentless march toward randomness may be what gives time its forward direction. But then there is the quantum world. The phenomenon of quantum entanglement suggests an instantaneous connection between particles, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to operate outside our normal rules of spacetime, challenging our understanding. The quest to understand time is far from over. New theories are exploring whether time is fundamental at all, or an emergent property of something deeper. Our understanding of time is still evolving, waiting patiently for us to catch up. So, let's bring the story back to you. The metronome we imagine in our heads, ticking away the years, is an illusion. The reality is quieter and stranger. Time is not a rigid track we all travel on together. It is more like a flowing river, and each of us is in our own boat, navigating a unique path. Every car ride, every airplane trip, every step you take, is a small change in your course through that river. You are constantly altering your personal journey through space-time. The person you were a year ago has aged a slightly different amount than a friend who lives in a different city. The differences are microscopic, but they are real. Your body is a time machine. Not a machine of flashing lights, but one made of flesh and bone, powered by the quiet and beautiful laws of the cosmos. With every move you make, you are its pilot, charting your own, unique course through the grand and mysterious dimension we call time. Your life is not just a duration, it is a journey through space-time, and the path you take is yours and yours alone. Thank you for joining us on this journey through space-time. If you enjoyed this, you might also like our video on the twin paradox or our exploration of what's inside a black hole. You can find those right here. Until next time, keep looking up, and keep asking questions. Your GPS is living in the future. Every time you use your phone to find your way, to see the quickest path to work, or to discover a new place, you're taking part in a silent, invisible conversation. A conversation with a group of satellites, moving quietly in orbits thousands of miles above your head. You ask a simple question: where am I? And in less than a second, they provide an answer. We accept this process without much thought. We press a button on a screen, a map appears, and a small blue dot marks our position. It feels simple. It feels normal. But the reality behind it is anything but. This small, daily miracle is only possible because we account for one of the most profound truths about our universe. The simple act of your GPS working correctly is a constant, real-world proof of Albert Einstein's theories of relativity. Because here is the part that sounds like it belongs in a story, not in our daily lives. Those satellites that guide you are living in the future. For them, time is literally moving faster than it is for you, down here on the surface of the Earth. And if we did not know this, if we did not precisely account for this subtle quirk of the cosmos, your GPS would become useless. Not in a year or a month, but in a matter of hours. The blue dot on your map would drift by miles every single day, placing you in lakes, through buildings, and over cliffs. So, how does a century-old theory about the nature of space and time save your daily commute? How does gravity warp the flow of time itself? To understand this, we need to look at the secret life of your GPS, and in doing so, explore the very fabric of spacetime itself. It all comes down to an effect called time dilation. A name that sounds complex, but describes a simple, yet world-altering idea. The rate at which time passes is not constant. It is relative. It changes depending on how fast you are moving, and how strong the gravity is around you. For the GPS satellites, their clocks run ahead of ours on the ground by about 38 microseconds every day. That's 38 millionths of a second. It sounds like nothing, an amount of time too small for a human to perceive. So why does it matter? Because GPS is a system built on time. A tiny error in time becomes a massive error in distance. If we didn't correct for those 38 microseconds, your location would be wrong by about 11 kilometers, roughly 7 miles, after just one day. Tomorrow, it would be 14 miles off. The day after, 21. This isn't a theoretical problem, it's a practical one that had to be solved. And the solution lies in a quiet contest between two different parts of Einstein's work. The everyday marvel: how GPS should work. Before we explore how time can be stretched and squeezed, it is worth appreciating the simple elegance of the global positioning system in a world where time is absolute. Imagine a universe without relativity. In this world, how does your phone know where it is? The system is based on a very old idea. If you know your distance from several known points, you can find your exact location. For GPS, the known points are a constellation of about 31 active satellites, orbiting the Earth at an altitude of roughly 20,200 kilometers. Each of these satellites is, in essence, a clock of almost impossible precision, hanging in the sky. Think of it like this. Each satellite is constantly sending out a radio signal that contains two pieces of information: its name and the exact time. It says, "My name is Satellite Alpha, and the time is exactly 12 hours 0 minutes and 0 seconds. 0.00000000." Your phone, or a GPS receiver, picks up this signal. It looks at its own clock and notes the time it received the message, perhaps 12 hours 0 minutes and 0 seconds. 0.0673333333. The difference is the travel time. In this case, about 0.067 seconds. Since we know the speed of the signal, the speed of light, we can do a simple calculation. Distance equals speed multiplied by time. This tells your receiver that it is exactly 20,200 kilometers away from Satellite Alpha. This is not enough to know your location. It just means you are somewhere on the surface of a giant, imaginary sphere with satellite Alpha at its center. Now, your receiver listens for another satellite, Bravo. It calculates its distance to satellite Bravo, perhaps 21,000 kilometers. You are now on the surface of a second sphere. The intersection of two spheres is a perfect circle. You have narrowed your location from anywhere on the planet to somewhere along that circle. We're getting closer. Your receiver hears a third satellite, Charlie, and calculates its distance to be 19,500 kilometers. The intersection of our circle with this new, third sphere gives us just two possible points. One of these points is usually in a location that makes no sense, like deep inside the Earth, so it can be easily discarded. And just like that, with 3 signals, your receiver has found your position. In reality, your receiver listens to a 4th satellite, or even more. That 4th signal is not just for extra precision. It is to solve for the biggest unknown in the equation, your own clock. The clocks on the satellites are marvels of engineering. The clock in your phone is not. That 4th measurement allows the receiver to solve for the exact, correct time, letting your simple phone clock synchronize perfectly with the master clocks in orbit. This whole beautiful, intricate process relies on a single, unwavering assumption that a second in orbit is the same as a second in your hand. But it isn't. And that is the hidden problem, the quiet wrench in the gears of this otherwise perfect machine. The hidden problem. A tale of two relativities. The engineers who designed the GPS program in the 1970s knew that timing had to be almost unimaginably precise. To get a position accurate to within a few meters, the system needs to know the time to an accuracy of 20 to 30 nanoseconds, billionths of a second. They equipped the satellites with atomic clocks, the most stable timekeeping devices ever created. But some physicists on the project raised a quiet concern. They brought up Albert Einstein. They warned that according to his theories, the steady ticking of those clocks in orbit would be fundamentally warped from our perspective on the ground. This was not one problem, it was two, pulling in opposite directions. A cosmic tug-of-war was about to play out, 12,550 miles above the Earth. The first problem came from Einstein's special theory of relativity from 1905. This is the theory that deals with the relationship between space and time for objects in motion. One of its most famous predictions is that the faster you move through space, the slower you move through time relative to someone standing still. The GPS satellites are not stationary. They move at about 14,000 kilometers per hour. From our view on Earth, their clocks should appear to tick just a little bit slower than our own. The second problem came from Einstein's general theory of relativity his masterpiece from 1915. This theory describes gravity not as a force, but as a curvature of spacetime caused by mass. One of its key predictions is that time runs slower in a stronger gravitational field. The weaker the gravity, the faster time flows. The GPS satellites are orbiting far above us, where the Earth's gravity is much weaker. According to general relativity, this means the clocks on the satellites should appear to tick faster than our clocks on the ground. So, we have two effects, born from the same mind, predicting opposite outcomes. Special relativity says the satellite clocks should tick slower. General relativity says they should tick faster. Which one wins? The entire global positioning system depends on getting the answer exactly right. To find that answer, we need to look into each of these ideas more closely. Special relativity and the twin paradox. Let's start with speed. The core idea of special relativity began with a simple, observed fact. The speed of light in a vacuum is constant for everyone, no matter how they are moving. This sounds simple, but its consequences are profound. If the speed of light is absolute, something else must be flexible. That something, Einstein realized, is time itself. To picture this, we can use a thought experiment called a light clock. Imagine a clock that keeps time by bouncing a particle of light, a photon, between two mirrors. Each bounce is one tick. If you're standing still, you see the photon moving straight up and down. A simple path. Now, let's put that clock on a spaceship moving past you at high speed. From your perspective, as the photon travels from the bottom mirror to the top mirror moves to the side. So, from your point of view, the photon travels a longer, diagonal path. Here is the important part. We both agree on the speed of that photon. It's the speed of light. But from your perspective, the photon on the moving clock is traveling a longer distance for each tick. If the speed is constant but the distance has increased, then the time for each tick must also increase. The moving clock, from your point of view, is ticking slower. Time itself is passing more slowly for the moving clock. This leads to the famous twin paradox. Imagine two twins. One, Tara, stays on Earth. The other, Stella, travels to a nearby star at nearly the speed of light and then returns. For Tara on Earth, the trip might take 32 years. But for Stella, moving through space, time flows more slowly. When she returns after what she experienced as a 10-year journey, she finds that her twin sister is 32 years older, while she has only aged 10. Stella has quietly traveled into the future. This is not just a thought experiment. It has been proven. In 1971, in the Haffel-Keating experiment physicists flew ultra-precise atomic clocks on commercial airplanes around the world. As predicted, when moving at high speeds, the clocks ran slightly slower than a clock on the ground. Time had stretched, just as Einstein said it would. We also see this with particles called muons created in the upper atmosphere. They have a very short lifespan, and should not exist long enough to reach the ground. And yet, we detect them. This is because their high speed slows down their internal clocks, stretching their existence long enough to make the journey. So, back to our GPS satellites. They are moving at 14,000 kilometers per hour. This is fast enough to produce a measurable effect. According to special relativity, the satellite clocks should lose about 7 microseconds every day compared to clocks on the ground. It's a tiny amount, but it's real. But it is not the only effect at play. General relativity and the gravity well. 10 years later, Einstein proposed that gravity is not a force, but a result of mass bending the very fabric of spacetime. The common analogy is a stretched rubber sheet. A heavy bowling ball placed in the center creates a dip. If you roll a marble across the sheet, it follows the curve created by the ball. That, falling into the dip, is what we perceive as gravity. But Einstein's theory went further. It said that gravity curves time as well. The deeper you are within a gravitational well, the closer you are to the massive object, the slower time passes. Time literally flows more slowly at sea level than it does on top of a mountain, because the mountain top is slightly farther from the center of Earth's mass. This, too, is a measured fact. In 1959, the pound Rebka experiment proved it. Physicists sent a beam of gamma rays from the basement of a building up to the roof, 22.5 meters higher. As the light traveled upward, moving from stronger gravity to weaker gravity, it was moving into a region where time flows faster. This caused a tiny, measurable change in the light's frequency, perfectly matching Einstein's predictions. The effect is incredibly small on human scales. But over geologic time, it adds up. The Earth's core, sitting in the deepest part of our planet's gravitational well, experiences time more slowly than the surface. Calculations suggest that over the 4.5 billion year history of our planet, the core is about 2.5 years younger than the crust. So now we can return to our GPS satellites. They orbit far above us, where the gravitational field is about 4 times weaker than what we feel on the surface. According to general relativity, this means time for the satellites should be moving ahead of ours. The math shows that because of this weaker gravity, the clocks on GPS satellites should gain about 45 microseconds every single day relative to clocks on the ground. Now we have both pieces of the puzzle. Section 5. The consequence, the 11 kilometers daily disaster, asterisk. We have two relativistic effects, pulling in opposite directions. 1. Special relativity, speed, asterisk, causes the satellite clocks to run slower by about ***7 microseconds per day. 2. General relativity, gravity, asterisk, causes the satellite clocks to run faster by about **45 microseconds per day. The effect of gravity is much stronger than the effect of speed. To find the final result, we combine the two numbers. A gain of 45 microseconds minus a loss of 7 microseconds gives us a net gain of *38 microseconds per day. Every day, the clocks on every GPS satellite get ahead of the clocks on Earth by 38 millionths of a second. Again, this seems like nothing. But in the world of GPS, it is everything. Your receiver calculates distance by multiplying the signal's travel time by the speed of light, which is a very large number, about 300 million meters per second. If we ignore that 38 microsecond drift, after just one day, the time error gets built into the distance calculation. Distance error equals 300 million meters per second times 0.000038 seconds. Distance error equals 11,400 meters. That is 11.4 kilometers. Just under 7.1 miles. After only 24 hours of ignoring relativity, every GPS position on Earth would be wrong by more than 11 kilometers. Your home would appear to be in the next town over. A navigation app would confidently send you into a forest or a river. The system would be catastrophically broken. This was not a hypothetical problem. It was an immediate, system-breaking flaw. Had it not been accounted for from the very beginning, the system would have failed within its first day. The genius solution and the big picture. So, how is this problem solved? The answer is beautifully simple. The engineers knew the clocks were going to run fast by a precise, known amount. So, they deliberately built the clocks wrong. Before a satellite is launched, its onboard atomic clock is tuned to run slow. On the ground, it ticks at a rate that is slightly but precisely incorrect. But once the satellite reaches its orbit and is moving at its final speed, the two relativistic effects begin. The speed tries to slow the clock down, and the weak gravity tries to speed it up. And the combination of these two effects speeds up the slow-running clock by exactly the right amount. The wrongness on the ground is perfectly cancelled out by the reality of spacetime in orbit. From our perspective here on Earth, the clock on that satellite now appears to tick at the exact same rate as the master clocks on the ground. And so, we come full circle. The little blue dot on your screen stays in the right place because over a century ago, a man looked at the universe and asked, what if time isn't absolute? That seemingly abstract question led to a theory that not only reshaped our understanding of the cosmos, but also became an essential tool for modern life. Your GPS is living in the future, but thanks to the genius of Albert Einstein and the engineers who trusted his vision, it sends us messages that are perfectly in sync with our present. It is a quiet, daily reminder that the most abstract science can have the most profound and practical results. The next time you check your map, take a moment. You are not just finding your way. You are witnessing the subtle harmony of spacetime itself, a harmony that guides you, silently and perfectly, to where you need to go. The story of GPS is more than a story about technology. It is a story about human curiosity and our relentless need to understand the universe's rules. It proves that there is no such thing as useless knowledge. The patient work of theoretical physicists, wrestling with abstract equations, can lay the foundation for technologies that redefine our world generations later. From the twin paradox to the Earth's younger core, Relativity reveals a universe where time is not a rigid metronome but a flexible, flowing river. And by understanding how to navigate that river, we have managed to build a system that tells us exactly where we are, and in doing so, reminds us of how far our understanding has come. The nature of time explained slowly. Time feels like a quiet, constant presence. A steady rhythm that carries us forward, from one moment to the next. It is the invisible current on which we travel from birth, through life, and toward a future we cannot see. We measure it, we follow it, we wish for more of it. This simple, forward movement is one of the most fundamental parts of being alive. But it is also a story, one that begins to change the more closely we listen. What if this intuition, as deep as it is only part of the picture? What if the steady, universal clock we imagine does not truly exist? In the wider universe, time is not a constant. It can be stretched and compressed. It flows at different rates all around us. Even on your own body, right now, time is passing at infinitesimally different speeds. This is not a journey to be rushed. We will slowly unravel what time appears to be, from the orderly universe of our ancestors to the unfamiliar realities revealed by modern physics. In doing so, we will approach one of the most quiet and profound questions we can ask. Could time, anywhere in the universe, ever truly stand still? The answer is not a simple yes or no. It is stranger, and it asks us to reconsider what past, present, and future really mean. The clockwork universe we thought we knew. For a long time, the human idea of time was one of quiet order, as clean and predictable as a well-made clock. This idea found its clearest expression in the work of Sir Isaac Newton. In his Principia Mathematica, Newton described the laws of motion that would form the foundation of physics for more than 200 years. But to describe motion, he first had to define the stage on which it occurs: space and time. Newton's concept was elegant and, to us, deeply intuitive. He called it absolute, true, and mathematical time. In his view, time existed on its own, independent of anything happening in the universe. It was a single, cosmic metronome, ticking at the same constant rate for every person, every planet, and every star. Now, on Earth was the same, now, in the Andromeda galaxy. This absolute time, he wrote, of itself, and from its own nature flows equably without regard to anything external. This is the time of our daily lives. When we schedule a meeting, we assume our present moment is the same as everyone else's. Our global systems of communication and travel are built on this shared assumption. Newton made a distinction between this invisible, absolute time and what he called relative time, which is what we actually measure with our clocks. We observe the sun's movement, a pendulum's swing, or a crystal's vibration, and from these motions, we infer the passage of time. But to Newton, these were all just imperfect reflections of a true, underlying time that flowed serenely in the background, a rigid framework for reality. This idea of a universal time is so deeply a part of our thinking that it feels less like a theory and more like a self-evident truth. It is the silent backdrop to every memory and every plan. We see time as a single line, and all of existence moves along it together. The universe, in this view, is a grand clockwork mechanism, and time is its master gear, turning at a steady, predictable pace for all. For more than 2 centuries, this was the unshakable foundation of physics. It worked perfectly. Newton's laws could predict the path of a cannonball and the orbit of a planet with breathtaking accuracy. The universe seemed rational and orderly. But this beautiful, comforting picture was about to be unsettled. The person who would change it was a young patent clerk in Bern, Switzerland, who asked a simple question about light. That question would not just bend our understanding of time, it would break it apart. The unraveling, Einstein's revolution. At the turn of the 20th century, a quiet contradiction sat at the heart of physics. A set of equations by James Clerk Maxwell, which described electricity, magnetism, and light, contained a strange implication. They predicted that the speed of light in a vacuum was a constant, around 300,000 kilometers per second. This was not strange on its own, but the equations implied this speed was the same for every observer, no matter how fast they were moving. This went against all intuition. If you are on a train moving forward and you throw a ball, you expect the ball's speed to be its own speed plus the speed of the train. But experiments showed this wasn't true for light. Whether you are standing still or piloting a rocket, if you measure the speed of a passing light beam, you will always get the exact same number. Albert Einstein took this strange fact not as a problem, but as a fundamental principle of the universe. In 1905, with his theory of special relativity, he explored what it meant. And the most profound consequence was that if the speed of light is absolute, something else must be relative. That something was time. Part 1. The faster you go, the slower time flows. To understand why, we can use one of Einstein's own thought experiments. Imagine a clock made of two mirrors with a beam of light bouncing between them. Let's say the mirrors are positioned so that it takes the light exactly half a second to travel from one to the other, and another half a second to return. Each round trip is one tick of our clock, lasting 1 second. Now, let's put this clock on a spaceship and watch it fly past at a very high speed. For someone on the spaceship, the clock is normal. The light is just going up and down, ticking away 1 second at a time. But from our perspective on the ground, things look different. We see the spaceship moving horizontally. As the light leaves the bottom mirror, the top mirror moves forward. To reach it, the light has to travel on a longer, diagonal path. On its way back down, the bottom mirror has also moved, so the light travels on another diagonal path to return. The path the light takes as seen by us is clearly longer than the simple up and down path seen by the person on the ship. Here is the crucial point. Both we and the person on the ship must agree on the speed of light. Since we see the light traveling a longer distance, but its speed must remain the same, there is only one possible conclusion. For us, it must take more time. From our point of view, the tick of the moving clock takes longer than 1 second. Time itself, for that moving clock, has slowed down. This is not a mechanical failure of the clock. Time itself is passing more slowly for the spaceship and everything on it, relative to us. This effect is called time dilation. At everyday speeds, the change is too small to notice. But as an object approaches the speed of light, this slowing becomes dramatic. If it were possible for the spaceship to reach the speed of light, its time, from our perspective, would seem to stop completely. This is a measured, verified reality. GPS satellites orbit the Earth at high speeds, and their clocks run slightly slower than clocks on the ground because of this effect. If engineers did not account for this, the GPS system would become inaccurate by several kilometers every day. Particle accelerators accelerate subatomic particles to nearly the speed of light. These particles have very short lifespans, but at these speeds, their time slows down so much from our perspective that they survive long enough for us to study them. This leads to the twin paradox. If one twin stays on Earth while the other takes a round trip on a very fast spaceship, upon returning, the traveling twin will have aged less. This is not a paradox but a direct consequence of time's relativity. Each has experienced time passing normally in their own frame of reference, but their journeys through spacetime have been different. Part 2. Gravity's heavy hand on time. A decade after revealing that speed affects time, Einstein deepened the revolution with his theory of general relativity. This time, he looked at gravity. Newton had described gravity as a mysterious force acting between two objects. Einstein offered a different picture. He proposed that space and time are not separate, but are woven together into a single, four-dimensional fabric, spacetime. Massive objects, in this view, warp this fabric. Imagine a flat rubber sheet. If you place a heavy ball in the center, the sheet curves. A marble rolled nearby will then follow that curve. According to Einstein, this is what gravity is. Planets and stars don't pull on other objects. They bend the spacetime around them, and other objects simply follow the contours. The Earth orbits the Sun because it is moving along a straight line through spacetime that has been curved by the Sun's mass. This geometric view of gravity led to another strange prediction. Just as high speed slows time down, so does being in a strong gravitational field. Time runs slower in regions of higher gravity. This is known as gravitational time dilation. The deeper you are in a gravitational well, the slower your clock will tick relative to a clock farther out. This effect is happening to you right now, in a minuscule but real way. Your head is slightly farther from the Earth's center of mass than your feet are. This means your head is in a slightly weaker gravitational field. The result is that time passes ever so slightly faster for your head than for your feet. The difference is almost unimaginably small, but it has been measured. In 2010, physicists used hyper-precise atomic clocks to measure this difference over a height of just 33 centimeters. The effect is much more noticeable for our GPS satellites. While their high speed slows their clocks, their higher altitude, where gravity is weaker, speeds their clocks up by a greater amount. The net result is that the satellite clocks run faster than clocks on the ground by about 38 microseconds daily. This correction must be programmed into the system for it to function. Einstein had completely dismantled Newton's clockwork universe. There is no single, universal time. Each observer's experience of time is local, shaped by their motion and their position in a gravitational field. Time is not a rigid ruler but a flexible ribbon, stretched by speed and squeezed by gravity. We've seen how our intuitive idea of time begins to break down. Time is not the steady river we imagined, but a much stranger landscape. If this kind of calm exploration into the fabric of reality helps you unwind, consider liking the video and subscribing to the channel. The path ahead gets even quieter and even more strange. The arrow of time. Why yesterday is always behind us. Einstein's theories revealed that time was malleable, but they did not explain its direction. The equations of physics, including Einstein's, work just as well forwards in time as they do backwards. At the microscopic level, there is no preferred direction for time. A video of two particles colliding would look perfectly normal if played in reverse. And yet, in our world, time clearly has a powerful direction. We call this the arrow of time. An egg breaks, but it does not unbreak. An ice cube melts in a warm drink, but we never see a lukewarm drink spontaneously form an ice cube. We remember the past, but we do not remember the future. Why is there such a clear difference between past and future in our experience, when the fundamental laws of physics seem not to care? The answer, physicists believe, is found not in the laws of motion, but in the laws of probability, in a concept called entropy and the second law of thermodynamics. Entropy can be thought of as a measure of disorder. The second law of thermodynamics states that in an isolated system, the total entropy, or disorder, will always increase or stay the same over time. It never decreases. Imagine a quiet room. There is perhaps only one way for it to be perfectly ordered. Every book on its shelf, every object in its place. But there are countless ways for it to be disordered. A book on the floor, a cup left out, dust settling on a surface. Over time, through random chance alone, the room is statistically far more likely to move toward one of the many disordered states than toward the single ordered one. The universe seems to be no different. Systems naturally evolve from states of low entropy, order, to states of high entropy, disorder, simply because there are vastly more ways to be disordered. An egg is a highly ordered structure. When it breaks, it becomes a disordered mess. It's not that the laws of physics forbid the atoms of the broken egg from reassembling themselves. It's just that the number of ways for those atoms to be a messy puddle is astronomically larger than the one specific arrangement that makes a whole egg. The odds are so overwhelmingly against it that it is, in practice, impossible. This quiet, relentless increase in entropy is what gives time its arrow. The reason we see ice melt and rooms get messy is because the universe as a whole is moving from a state of lower entropy to a state of higher entropy. The future is simply the direction of greater disorder. The past is the direction of greater order. This raises a deeper question. If the universe is always getting more disordered, then it must have started in a state of incredible order. Our cosmological observations confirm this. The Big Bang, which began our universe 13.8 billion years ago, appears to have been a state of remarkably low entropy. At the very beginning, the universe was incredibly hot, dense, and uniform. While that might sound chaotic, in a universe ruled by gravity, a smooth, uniform state is actually a very low entropy, highly ordered configuration. A much higher entropy state is one where gravity has pulled matter into clumps, forming stars, galaxies, and eventually, black holes. So, the arrow of time we experience is a direct consequence of the initial condition of our universe. We live in the aftermath of that low entropy beginning, carried along on a cosmic wave of increasing disorder. Even our ability to form memories is tied to this process, linking our minds to a past that was more ordered than the present. This gives time its one-way street feel. But this brings us back to our ultimate question. We know time can be slowed. We know it has a direction. But could this forward march ever come to a complete stop? To answer that, we must travel to the most extreme environments the universe has to offer. The edge of understanding, where time appears to stand still. We return to our central question. Can time stop? From a physical standpoint, the idea is almost a contradiction. Time is a measure of change. We know an object is moving because at different moments in asterisk time, it is in different positions in asterisk space. If time were to stop, all change would cease. Motion would be impossible. The atoms in your body would freeze. The photons of light carrying information to your eyes would halt. It would be a universal pause. The laws of physics as we know them do not seem to permit this. But the universe contains places where these laws are pushed to their absolute limits. These are black holes. A black hole is what remains when a massive star collapses under its own gravity, crunching matter down into a point of theoretically infinite density called a singularity. Its gravity is so powerful that it warps spacetime to an extreme degree. Beyond a certain boundary, nothing, not even light, can escape. This boundary is called the event horizon. It is here, at the edge of the event horizon, that our understanding of time is truly tested. Imagine you are in a spaceship, hovering a safe distance from a black hole. You watch as a colleague, Sally, in her own ship, drifts toward it. As she approaches the event horizon, gravitational time dilation becomes extreme. From your perspective, something very strange begins to happen. Sally's ship appears to slow down. If she sends you a light signal every second by her clock, the interval between the signals you receive will grow longer and longer. Her progress toward the event horizon seems to grind to a halt. The light from her ship is stretched by the intense gravity, a process called gravitational redshift. Her ship appears to you to become redder and redder, fading from view. It shifts from visible light to infrared, then microwaves, then radio waves, becoming dimmer until it is undetectable. From your vantage point, Sally will appear to slow, fade, and freeze as she approaches the event horizon. You could watch for the entire age of the universe, and you would never see her cross it. From the outside observer's perspective, time for the falling object appears to stand still at this boundary. But what does Sally experience? For her, nothing special happens at the moment she crosses the event horizon. Her clock continues to tick at 1 second per second. She sails smoothly across the boundary, unaware she has passed the point of no return. For her, time does not stop. It does not even slow down. So, who is right? Is she frozen in time for eternity, or did she fall through in an instant? The quiet, astonishing answer from general relativity is that both are true. Reality is relative. Your reality, as the distant observer, is that she is forever at the event horizon. Her reality is that she has fallen inside. This is a fundamental consequence of how spacetime is warped. There is no single, objective reality to the situation. Once inside, her fate is sealed. The warping of spacetime is so extreme that the direction toward the singularity becomes as inevitable as the future is for us. For her, space and time have effectively swapped roles. She can only move toward the singularity. As she approaches it, time dilation becomes even more extreme. Seconds for her could be equivalent to billions of years passing in the outside universe. And at the singularity itself? Here, our science falls silent. The equations predict a point where the laws of physics as we know them break down. We simply do not know what happens to time there. It might cease to exist. It might become something else. This is the true edge of our understanding, where a new theory is needed to guide us. So, can time stop? The answer is a quiet paradox. From an external view, time for an object falling into a black hole appears to stop. But for the object itself, time flows on. Time never truly stops in any single frame of reference. The block universe. Is the future already written? The strange relativity of time invites us to consider a different, more permanent vision of reality. It's a concept known as the block universe, or eternalism. Our intuitive view of time is that only the present moment is real. The past is gone. The future is not yet formed. The now is a special moment that moves forward, turning possibility into history. But relativity challenges this. If two observers, like you and Sally at the black hole, can have different realities about what is happening now, it suggests that a universal now is an illusion. What one person measures as simultaneous, another person in a different state of motion can measure as happening at different times. The block universe interpretation takes this to its logical conclusion. It suggests that if time is another dimension, woven together with space, then perhaps we should treat it like space. You accept that other places exist even if you are not there. The block universe asks us to consider that other times exist in the same way. In this model, all of time, every moment from the Big Bang to the end of the universe, exists simultaneously. The past, present, and future are all equally real, laid out in a static, four-dimensional block of spacetime. The dinosaurs, your birth, and this present moment are all just different coordinates in this block. In this view, the flow of time is an illusion of human consciousness. Our awareness moves through this block, experiencing one slice of spacetime after another, creating the sensation of passage. But the timeline itself is fixed. The future is no less real than the past, it is just a region of spacetime our consciousness has not yet reached. This has quiet, staggering implications. If the future already exists, does that mean our choices are an illusion? Physicists and philosophers are not in agreement here. Some argue the block universe is the most direct interpretation of relativity. Others find it so contrary to our experience of an open future that they believe our understanding is still incomplete. The block universe isn't a proven fact, but a profound idea that follows from the physics we've explored. It represents the ultimate departure from our simple view of a flowing river of time. It suggests that reality might be a static, timeless crystal, and our lives are just a specific path traced through its intricate structure. Our journey began with the simple feeling of a ticking clock. We end with a vision of time as something woven into the fabric of the universe itself. We learned that the forward arrow of our lives is likely a consequence of the universe's quiet journey towards disorder. We stood at the edge of a black hole and found that while time can appear to freeze from the outside, it marches onward for anyone who takes the plunge. The universe, it seems, does not permit an absolute stop. It presents us with different realities, all true from their own perspective. We are left with a new picture of time. It is not a simple line, but a vast, complex landscape. Our human experience of a flowing now is a meaningful part of our reality, but it may be just one limited perspective on a much grander structure. The deepest questions remain. We still do not fully know why the universe began in such an ordered state, or what happens in a singularity where time's story seems to end. Time is not just a clock on the wall. It is the geometry of the cosmos, the engine of entropy, and perhaps, the structure of all that has been and ever will be. The journey to understand it is a journey to understand reality itself. And the mystery continues. If you want to continue this calm exploration into the nature of reality, consider subscribing to the channel. Thank you for taking this slow journey with us. Title: We finally found the edge of reality, hook. What if I told you the universe has a speed limit? Not for how fast you can go, but for how fast time itself can move. What if the relentless march of moments we all feel isn't some smooth, flowing river, but a series of tiny, discrete steps, like frames in a movie? And what if I told you that in a lab, right now, physicists have witnessed an event so fleeting, so impossibly fast, it pushes right up against the boundaries of reality as we know it? This isn't science fiction. This is the story of what happens when the universe's internal clock can't tick any faster, and we get a glimpse of the edge of time itself. The old world. For most of human history, time was just there. It was the rhythm of the sun and moon, the turning of the seasons, the beat of your own heart. We tried to track it with dripping water, falling sand, or a swinging pendulum. To the great Sir Isaac Newton, time was absolute. He imagined a single, universal clock, ticking at the exact same rate for everyone, everywhere. It was a cosmic metronome, marching forward with cold, mathematical precision. In this view, time was the one thing you could count on to be constant. Then, a young patent clerk in Switzerland completely shattered that idea. Albert Einstein, with his theories of relativity, showed us that time isn't absolute at all. It's personal. It's flexible. He proved that time can stretch and shrink, warped by gravity and bent by speed. For an astronaut flying near the speed of light, time literally slows down. For a GPS satellite orbiting Earth, time ticks just a tiny bit faster than for us down on the surface. Einstein showed us that time isn't a rigid ruler, but a malleable fabric, woven together with space. This was a complete revolution in thought. It yanked time out of the realm of philosophy and put it squarely into the world of physics. We got incredibly good at measuring it, moving from clunky mechanical clocks to the vibration of quartz crystals, and finally, to the hum of atoms themselves. Today, our atomic clocks are so precise they won't lose a single second in billions of years. They define our second based on exactly 9,192,631,770 vibrations of a cesium atom. We became the masters of the second, the millisecond, the microsecond. We thought we had tamed time. But even as we were celebrating, a much weirder question started bubbling up from the world of quantum mechanics, the physics of the very, very small. While Einstein's universe was smooth and curved, the quantum world was all about jumps, probabilities, and uncertainty. And it hinted at something wild. That maybe time, just like matter and energy, wasn't infinitely divisible. Maybe, if you could zoom in far, far enough, past the ticks of our best clocks, you'd find that the smooth river of time dissolves. You'd discover that reality isn't a continuous film, but a series of individual frames. A universe with a fundamental refresh rate. This was a mind-bending idea that lived mostly in the equations of theoretical physicists. Until now. Because in a lab in Germany, scientists have finally captured a glimpse of one of those frames. They've measured something so brief, it brings us to the very edge of that theoretical limit, to a place where the clock of the universe stutters, and our whole understanding of reality starts to get weird. The discovery. The story starts in a massive, futuristic facility in Hamburg, Germany called the Petra 3. You can think of it as a giant racetrack, 2.3 kilometers around, where electrons are blasted to nearly the speed of light. Powerful magnets then force these electrons to screech, giving off some of the most brilliant and energetic X-rays on the planet. It's a place built to see the unseeable. And a team of physicists from Goethe University, led by Reinhard Durner, had a question they wanted to answer. How long does it take for light to cross a single molecule? Now, that sounds simple, but it's a really profound question. It's not just about speed, it's about how things happen. When a particle of light, a photon, hits a molecule, does the whole thing react instantly, as one solid unit? Or does the news that a photon has arrived have to travel across the molecule? The team bet on the latter, that even inside a molecule, nothing can travel faster than the speed of light. But to prove it, they had to measure a slice of time so small it was considered unmeasurable. Their target was the simplest molecule there is, hydrogen, H2. Just 2 protons and 2 electrons. The plan was to fire a single, perfectly tuned X-ray photon at the molecule with just enough energy to kick both of its electrons out. The photon would hit one side of the molecule, booting out the first electron. Then, a split second later, its influence would be felt on the other side, kicking out the second electron. That time delay between the 2 ejections would be the time it took for the photon's influence, for light itself, to travel the length of that tiny, tiny molecule. To see this happen, they needed a special kind of camera. Not one with lenses and film, but a ridiculously sophisticated particle detector called a COLTRIMS reaction microscope. This beast can detect the individual particles flying out of the collision, the electrons and what's left of the hydrogen, and measure where they went with unbelievable precision. And this is where the experiment gets really clever. In quantum mechanics, electrons aren't just little balls, they're also waves. When the 2 electrons got ejected, their waves spread out and interfered with each other, creating a pattern, like ripples in a pond. This interference pattern is super sensitive. If both electrons had left at the exact same instant, the pattern would have been perfectly symmetrical. But they didn't. Because the photon's influence had to travel from one atom to the other, the second electron was ejected a tiny moment later. And that tiny delay caused a slight skew in the interference pattern. By measuring that skewed pattern, the scientists could work backward. As study co-author Sven Grundmann put it, they used the interference of the 2 electron waves to precisely calculate when the photon reached the first and when it reached the second hydrogen atom. The number they came up with is just bonkers. 247 zeptoseconds. Let's try to get our heads around that. A zeptosecond is a trillionth of a billionth of a second. That's a decimal point, followed by 20 zeros, and then a 1. If you scaled up 1 second to equal the entire age of the universe, a zeptosecond would be just a couple of minutes on that cosmic timeline. The chemical reactions that power our bodies happen in femtoseconds, which are thousands of times longer than this. This wasn't just a new record, it was proof of a fundamental rule of the universe. As Professor Durner said, they saw for the first time that the electron shell in a molecule does not react to light everywhere at the same time. Information has a speed limit, even on the scale of a single atom. We had just witnessed the universe's internal lag. And we had clocked an event so fast that it borders on the theoretical limit of time itself, bringing us face to face with a universe that is not nearly as smooth as it looks. The implications. So, we measured 247 zeptoseconds. Cool number. But what does it actually mean? This discovery is more than just a world record. It's a key that opens a door to a much deeper, much weirder layer of reality, where our basic ideas about time and space start to completely fall apart. To get it, we have to go from the zeptosecond down to a scale that is, frankly, mind-breaking. A pixelated reality. Our journey into the weird starts with a guy named Max Planck, way back around 1899. Planck was struggling with a huge problem in physics that predicted hot objects should glow with an infinite amount of energy, which, obviously, they don't. To fix this, he came up with a wild idea. What if energy isn't continuous? What if it comes in tiny, discrete packets, which he called quanta? This was the birth of quantum mechanics, and it gave us a new magic number for the universe, the Planck constant. Planck realized he could take his constant, combine it with the speed of light and the constant of gravity, and cook up a set of fundamental units for length, mass, and time. These weren't arbitrary units like meters or seconds. They seemed to be baked into the very source code of the cosmos. Physicists sometimes call them God's units. The unit of length is the Planck length, and it's almost comically small. About 10 to the minus 35 meters. To put that in perspective, if you scaled up a single atom to be the size of the known universe, the Planck length would be about as tall as a tree. This is the scale where the smooth spacetime of Einstein is expected to completely break down. And that brings us to the Planck time. The Planck time is simply the time it would take light to travel one Planck length. It's about 10 to the minus 44 seconds. This number makes a zeptosecond look like an eternity. A zeptosecond is 10 to the minus 21. The Planck time is 10 to the minus 44. There are way more Planck times in a single second than there are seconds in the entire 13.8 billion year history of the universe. But the Planck time is more than just a tiny number. It's thought to be the shortest possible meaningful unit of time, the quantum of time itself. Why? Because to measure anything shorter, you'd have to use so much energy in such a small space that you would accidentally create a microscopic black hole. The universe would literally stop you by swallowing your experiment. It's the ultimate physical barrier. It suggests that time, at rock bottom, isn't a continuous flow. It's pixelated. Just like a digital picture is made of individual pixels, and you can't zoom in any further, spacetime itself might be made of indivisible blocks of Planck length and Planck time. Reality, in other words, might have a resolution. This is why the 247 zeptosecond discovery is so huge. We're still a long way from measuring a Planck time, but we're getting closer. We're peeling back the layers, and the fact that our theories are holding up at the zeptosecond scale gives us confidence that we're on the right track. It's a signpost on the road to the Planck scale, telling us that the deep weirdness of quantum gravity isn't just a fantasy. It's the next frontier. The end of cause and effect. We live our lives by a simple rule: cause and effect. A happens, which makes B happen. The past affects the present, which determines the future. This chain of causality is the arrow of time. The zeptosecond experiment is a perfect, lightning-fast example of this. The photon arrives, cause, and 247 zeptoseconds later, the electron gets kicked out, effect. It might be the fastest cause and effect relationship we've ever seen. But what happens when you get down to the Planck time? This is where things go from weird to completely mind-melting. At the Planck scale, the very concepts of before and after are thought to lose all meaning. Physicists like John Wheeler imagined that if you could zoom in to this level, you wouldn't see smooth spacetime. You'd see a chaotic, boiling mess known as quantum foam. Tiny rips, tunnels, and microscopic wormholes would constantly pop into and out of existence, bubbling with energy borrowed from nothing. In this chaotic foam, the neat sequence of cause and effect breaks down. An effect could appear to happen before its cause. The arrow of time would stop pointing in one direction and become a jumbled, probabilistic mess. The steady tick-tock of the clock would dissolve into a fizz. This isn't just a wild guess, it's a consequence of Heisenberg's uncertainty principle. It says that for very short time intervals, there can be huge fluctuations in energy. At the Planck scale, These energy fluctuations get so enormous that they warp and tear the fabric of spacetime itself, making the flow of time fundamentally uncertain. So the zeptosecond measurement is a landmark for two reasons. It's the sharpest confirmation of causality we've ever had. But at the same time, it brings us to the doorstep of a realm where causality might not even exist. It's like climbing a mountain to a record height, only to finally see the summit, where the air is too thin to breathe and the rules of biology break down. We've measured the edge of causality, and in doing so, we've caught our first real glimpse of the chaos that lies beyond. A new cosmic speed limit. We're all familiar with the universe's most famous speed limit. C*, the speed of light. It's the ultimate speed for anything in the cosmos. Nothing can travel faster. The Planck time suggests there's another, equally fundamental limit. Not a limit on speed through time, but a limit on the divisibility of time itself. It's a hard floor, a minimum interval. The zeptosecond discovery helps us see that these limits aren't just numbers in a textbook. They are active rules that govern reality. The fact that it took 247 zeptoseconds for light to cross a hydrogen molecule is a direct result of the speed of light being a real, physical barrier. Viewing Planck time as a new limit could mean that reality is, in a very real sense, digital. It would mean the smooth laws of physics we see are just an approximation that emerges from countless underlying quantum events, much like the smooth flow of water emerges from the jiggling of trillions of individual H2O molecules. This has huge implications for the holy grail of physics, a grand unified theory that unites Einstein's relativity with quantum mechanics. Relativity is built on smooth, continuous spacetime. Quantum mechanics works fine on that background. But at the Planck scale, they clash. Any successful theory of quantum gravity has to explain what's going on in this pixelated, foamy realm. Is reality made of tiny vibrating strings? Or a network of connected nodes? The zeptosecond measurement gives us a crucial piece of data. It stress tests our models in a new, extreme regime. And so far, they're holding up, pointing us ever more confidently toward that ultimate limit. The point where the clock of the universe doesn't just tick fast, but might stop ticking altogether. The new reality. So where does this leave us? We've gone from ticking clocks, down to a zeptosecond, and peered into the abyss of the Planck time. When we put it all together, the picture of reality that emerges is profoundly different from the one we experience. It's a reality that's granular, probabilistic, and fundamentally fuzzy at its core. The old world was analog, like a ramp. You can stand anywhere on it. Our intuition, and even Einstein's relativity, sees the universe this way: a smooth sheet with no seams or gaps. The new reality is digital, more like a staircase. You can be on one step or the next, but you can't be in between. The universe may not be infinitely divisible. The Planck length and Planck time suggest a fundamental pixel size for reality. Our zeptosecond measurement is the highest resolution photo we've ever taken of that reality, and we're just starting to see the hints of the graininess underneath. This forces us to ask a wild question. What if space and time aren't fundamental at all? What if they're emergent properties? Just as temperature is a statistical average of jiggling molecules, maybe time is a statistical average of something deeper happening at the Planck scale. The smooth flow of time we experience could be an illusion, a grand average of countless chaotic quantum interactions. A world without fundamental time is a world where the neat line from past to present to future might just be a feature of our human perception. Down in the quantum foam, there may be no arrow of time at all. Events might exist in a complex web of probabilities, not a simple timeline. The zeptosecond discovery at Petra 3 is a dispatch from this frontier. It tells us that our comfortable, classical world is an illusion. The true reality is a shimmering, uncertain, pixelated tapestry. We are living on the smooth surface of a deep and chaotic ocean. For centuries, we were happy just sailing the surface. Now, with tools like this, we've finally built a submarine that can peer into the depths. What we're finding there is stranger than we could have imagined. But it's the truth. Today, we've traveled to the very edge of time. We started with the familiar tick-tock of a clock, saw how Einstein turned it into a flexible fabric, and then plunged into the quantum realm, where physicists captured an event lasting just 247 zeptoseconds. This single measurement is a bridge, connecting the world we can measure to one we can only imagine. It confirms that the universe has rules, and those rules hold up even at the most extreme scales. But more than that, it points us toward the Planck time, the theoretical floor of reality, where time stops being a smooth river and becomes a series of discrete ticks. We've explored what it means to live in a pixelated universe, where cause and effect might break down and where time itself might be an illusion. We are living in an incredible time. The lines between what we know and what we don't know are constantly being redrawn. We've clocked an impossibly small moment, and in doing so, we've come face to face with the fundamental granularity of existence. It seems the universe has a refresh rate, and we're getting closer to seeing it. The journey doesn't stop here. The quest to understand time is the quest to understand reality. What will we find when we can resolve time even more sharply? Will we find extra dimensions? Will we see the quantum foam? Will we finally unlock the secrets of the Big Bang's very first moment? These are the questions that drive us forward. If this journey to the edge of reality sparked your curiosity, make sure you subscribe and hit the notification bell. There are so many more mysteries to explore, from the heart of a black hole to the beginning of time itself. Your brain is lying to you about time. There is a feeling, quiet and constant, of moving through time. A steady, forward march from one moment to the next. A moment ago is in the past. A moment from now is in the future. This sense is so fundamental, so deeply woven into how we exist, that questioning it can feel strange. But that feeling is not as simple as a universal, ticking clock. It is a story told by the mind. It is a story shaped by what we notice, what we remember, and what we feel. The way a week of discovery can feel immense in our memory, while a month of routine evaporates. That feeling is not just a trick of the mind. It is a clue, a quiet hint that the solid, dependable flow of time is more personal and more flexible than we have ever been taught. It suggests that our brain does not just measure time, in a very real way, it builds it. This is a journey into that idea. We will begin inside the mind, with the strange and subtle ways it constructs our sense of duration. And we will end at the edge of physics, where the very concept of time seems to dissolve, forcing us to wonder if the story our brain tells us about time is actually a deep reflection of how the universe itself works. Let's begin with an experience most of us share, sometimes called the holiday paradox. Think of a long vacation from years ago, or the summers of childhood. In memory, they can feel vast, filled with distinct moments and discoveries. Now, think about the last month. Unless it was unusual, it likely feels much shorter, a compressed block of familiar events. The actual duration on a calendar was longer, but the perceived duration was not. The reason for this has little to do with clocks, and everything to do with how the brain records experience. It does not act like a camera, capturing every moment equally. It acts more like a careful archivist, prioritizing what is new and significant. When we are young, almost everything is new. Each day is filled with novel information, and the brain works hard to process and store these experiences. This creates a dense library of memories. When we look back, the mind surveys this vast collection and concludes that the time must have been very long. An adult life filled with routine is different. The daily commute, the familiar work, the evening ritual. The brain, being efficient, does not need to create new, detailed records for these predictable events. It runs on a kind of autopilot. The library of new memories for that period is sparse. When we look back, the mind sees very little information and concludes the time must have been short. The duration we feel is not a measure of seconds and minutes, but a measure of novelty. This becomes even clearer in moments of shock or surprise. Scientists sometimes refer to this as the oddball effect. If you are shown a series of identical images, and then one different, unexpected image, the oddball, appears for the exact same amount of time, you will often feel it lasted longer. Your brain, jolted from its rhythm, dedicates a surge of resources to processing this new event. The resulting memory is richer and more detailed, and so it feels longer when we remember it. This helps explain why people in accidents often report that time seemed to slow down. The brain was not literally seeing the world in slow motion. Instead, in that moment of extreme danger, it began frantically recording every possible detail. The color of a car, the glint of light on glass. It was creating an incredibly dense memory, which, when replayed by the mind, feels as though it unfolded over a much longer period. But our sense of time is not just shaped by memory. It is also tied to our emotions and our body's own quiet rhythms. Take the difference between awe and fear. Studies have shown that experiencing awe, standing before a grand landscape, or watching a majestic natural event, tends to make people feel that time is abundant, passing more slowly. Awe expands our sense of the present moment. Fear can have an opposite effect. In anxious situations, our internal clock seems to speed up, stretching out the seconds. Participants in studies who were anticipating a mild electric shock consistently overestimated how long they were waiting. The feeling of dread made the time drag on. The very beat of your heart plays a part in this. The field of interoception, which studies how the brain interprets signals from the body, is revealing that our sense of time is tied to our pulse. In a fascinating study, researchers had participants listen to simple audio tones and judge their duration. They found that when a participant's heart rate was slower, they perceived the tones as being longer. The heartbeat acted as a kind of rhythmic frame, and a slower rhythm seemed to stretch the perception of what happened within it. But another study adds a layer of complexity. Researchers showed participants short videos designed to be pleasant, neutral, or unpleasant. They found something counterintuitive. When watching unpleasant or threatening content, the more a participant's heart rate slowed, the shorter they perceived the video to be. This is thought to be connected to the freezing response, an instinctual reaction to a threat where the body slows its metabolism. In this state of high alert, the brain's perception of time seems to shrink. Even more, the researchers found that this link was less stable in people with high levels of body dissatisfaction, suggesting our psychological relationship with our own bodies can change how we physically perceive reality. Our brain, then, is listening to our heart, but the story it tells about time depends on the context. This is not a simple clock, it is a dynamic, interpretive system. This idea goes back to the 1930s, with what is called the chemical clock hypothesis. The observation was that our judgment of time seems influenced by our body temperature. The general finding, supported by many studies, is that as our internal temperature goes up, our internal clock seems to speed up, making time feel like it's passing more quickly. This may be why, with a fever, an hour can feel like 20 minutes. Your body's metabolic rate provides a tempo for your mind. So our sense of time is built from a collage of inputs: the novelty of events, the density of memory, the input of emotion, the rhythm of the heart, and the temperature of the blood. The unwavering, linear flow we feel is an impression, created by the mind. But what if this flexible, personal construction of time is not a flaw? What if it is mirroring the way time actually works in the universe at large? For most of history, our intuition about time was captured by Sir Isaac Newton. He saw time as absolute and universal, a single cosmic clock ticking at the same rate for everything, everywhere. It was the rigid stage on which reality unfolded. This was the foundation of classical physics. It was elegant, simple, and it turned out to be incomplete. The first change to this picture came in 1905, from Albert Einstein. His theory of special relativity revealed that time is not absolute. It is relative to motion. The faster you move through space, the slower time passes for you compared to someone who is still. This isn't a theory in the speculative sense. It's a measurable property of our universe. Motion through space affects motion through time. 10 years later, with his theory of general relativity, Einstein showed that gravity can also warp time. Gravity, he explained, is the curvature of spacetime caused by mass. The stronger the gravitational field, the more it curves spacetime, and the slower time flows. This, too, is a physical reality we rely on every day. The proof is in the Global Positioning System, or GPS. The GPS network is a group of satellites, each with a very precise atomic clock. For the system to work, these clocks must stay synchronized with clocks on the ground. But the satellites are subject to both of Einstein's discoveries. First, they are moving at about 14,000 kilometers per hour. Due to special relativity, their clocks tick slower than ours by about 7 microseconds each day. Second, they are orbiting far above the surface, where Earth's gravity is weaker. Due to general relativity, this makes their clocks tick faster than ours by about 45 microseconds each day. When taken together, the clocks on GPS satellites get ahead of clocks on Earth by 38 microseconds every day. It seems like a tiny amount, but if engineers did not correct for this, GPS navigation would fail. Errors would accumulate at a rate of about 10 kilometers every single day. The fact that your phone can guide you to a destination is proof that time is not universal. It flows at different rates in different places. This leads to a strange and quiet interpretation of reality known as the block universe. If there is no universal now, then the distinction between past, present, and future may also be an illusion. This view suggests that all of time, every moment that has happened and ever will happen, exists at once. Reality is a four-dimensional block of spacetime, and our consciousness is like a spotlight moving through it, illuminating one slice after another, creating the impression of flow. For decades, this was the strangest vision of time physics had to offer. But a deeper puzzle was emerging, from the effort to reconcile Einstein's general relativity with quantum mechanics. Relativity describes the large-scale universe of gravity and spacetime. Quantum mechanics describes the small-scale universe of atoms and particles, and its standard formulation works as if there is a rigid, universal, Newtonian time in the background. The two theories are incredibly successful, but they are built on incompatible ideas about time. This is known as the problem of time. In the 1960s, physicists John Wheeler and Bryce DeWitt tried to unite the two theories. They formulated a single equation to describe the quantum state of the entire universe. The result was the Wheeler-DeWitt equation, and it contained a discovery so quiet and yet so profound, it changed physics. When they derived the final form of the equation, the variable for time, the letter t, was simply gone. The equation that was meant to describe the evolution of the universe had no time in it. It describes a static, timeless state. This suggested that at the most fundamental level, there may be no such thing as time. No past, no future, no flow. Just a static landscape of possibilities. Physics had arrived at a question that felt almost impossible to answer. If the universe is fundamentally timeless, where does the river of time we all experience come from? We are left with a quiet contradiction, a static, timeless universe in our deepest equations, and a dynamic, flowing universe in our own experience. How can both be true? Many physicists now believe the answer is that time is not a fundamental ingredient of the cosmos. It is an asterisk emergent phenomenon. It does not exist at the most basic level, but it appears at a larger scale. And the key to this emergence may lie in one of the most familiar laws of science, the second law of thermodynamics. This law states that in a closed system, entropy, a measure of disorder, tends to increase. A hot cup of coffee will always cool down as its heat dissipates into the room, increasing the overall disorder of the system. An egg will shatter, but the pieces will not reassemble themselves. This progression from order to disorder gives a clear direction to events. It is the only fundamental law of physics that distinguishes between past and future. Physicists call it the arrow of time. The past is a state of lower entropy. The future is a state of higher entropy. The Italian physicist Carlo Rovelli proposes that this thermodynamic arrow is the source of the time we perceive. He argues that time is a consequence of our blurred, macroscopic view of the world. He asks us to think about temperature. A single atom does not have a temperature. Temperature is a statistical property that only makes sense when you have a vast collection of atoms. It is their average energy. Rovelli suggests that time is like temperature. At the fundamental quantum level, there are only events, interactions between fields. There is no master clock. But we, as large beings, can never perceive this granular reality. We only see a statistical average of countless quantum interactions. From this blurring, this fundamental ignorance of the microstate, the phenomenon of entropy, and thus the flow of time, emerges. What we feel as the passage of time is a real, physical perception of the universe's irreversible movement toward greater disorder. This idea of emergent time is supported by another strange quantum phenomenon, entanglement. This is where two particles become linked, so that measuring one instantaneously influences the other, no matter how far apart they are. In 1983, physicists Don Page and William Wouters proposed that a timeless universe could still appear to evolve for an observer inside it. An internal observer, by becoming entangled with a part of the universe and using it as a clock, could then measure the rest of the universe and see it change relative to that clock. Time, in this view, is a relationship between entangled parts of a whole. For decades, this was a fascinating but theoretical idea. In 2013, a team of physicists led by Ekaterina Moreva found a way to test it. Their experiment was subtle and ingenious. They created a pair of entangled photons. In one scenario, an internal observer became entangled with one photon, using its changing state as a clock. From this perspective, the second photon appeared to evolve and change over time. In a second scenario, an external observer measured a property of the whole two-photon system without becoming entangled with either part. From this outside perspective, the system was completely static. It did not change. It was timeless. This was the first experimental demonstration that time can be an emergent property of entanglement. The evolution of the system depended entirely on the perspective of the observer. For the internal observer, entangled with a piece of the world, time emerged. For the external observer, who saw the whole picture, it vanished. We have traveled from the quiet workings of our own memory to the foundations of spacetime, and the picture that emerges is both subtle and transformative. The feeling of time is not a simple perception of an external reality. It is a complex construction, built by the brain from novelty, emotion, memory, and the rhythm of the body. And now, we see that the universe itself seems to operate on a similar principle. Physics has watched time shift from an absolute river, to a malleable stream, to something that seems to disappear entirely at the most fundamental level. The emerging idea is that time is not the container in which the universe happens. Time is a feature of what happens. It emerges from the irreversible unfolding of entropy, and from the intricate quantum relationships that connect the cosmos. So, the story your brain tells you about time is not a lie. Its deeply personal, flexible, and creative nature is not a flaw. It is a profound reflection of a deeper truth. That strange feeling of time flying by, or dragging to a halt, is your own consciousness connecting with the same quiet secret that physics is now uncovering. The universe isn't a story that happens in time. The universe is the story. Change is fundamental, and we are not just watching it unfold. We are processes of that change, and our perception of a past, a present, and a future is our unique way of reading the pages. If this exploration changed the way you think about your next moment, consider liking the video and subscribing to the channel. And I would be interested to know, what makes time seem to speed up or slow down for you? Feel free to share your own experiences with the strange nature of time in the comments below. The brain glitch that warps your reality. There is a quiet distortion in your perception of the world. It is a fundamental feature of the way you experience reality, and it happens every day. This is the reason 2 hours at a gathering of friends can seem to pass in an instant, yet 10 minutes in still traffic can feel like a much longer stretch of time. You have felt it, that quiet moment of looking at a clock and wondering where the time has gone. Or the opposite, watching a loading bar and feeling as if the seconds themselves are stretching, growing heavier. The reason for this is not in our watches, nor is it in the laws of physics. The answer is in the brain. For a long time, we have understood time as a constant, like a river flowing at a steady pace. But that is objective time. What we actually experience is something different, something neuroscientists sometimes call psychological time. It is a subjective version of reality, constructed quietly inside the mind. Today, we will explore the neuroscience of this internal clock. We will look at why our sense of time is an elaborate story, shaped by memory, emotion, and the chemistry of the brain. By the end of our journey, we will not just understand why time seems to quicken as we grow older, or slow in a moment of crisis. We will see that the brain is not just perceiving time, it is actively creating it. And once we understand the rules of this creation, we can begin to change our relationship with it. The elastic nature of moments. Before we explore the complex machinery inside the head, let us begin with the evidence we already know. The common, everyday moments when our sense of time seems to betray logic. These are the clues that our internal clock is not the steady instrument we might imagine. First, there is the experience of boredom. We have all been there. In a quiet waiting room. In a long lecture that seems to have no end. Or watching a microwave, as if a focused stare could somehow hasten the final seconds. In these moments, time does not just slow. It can feel thick and heavy. Every second announces itself. A minute can feel like 10. This is not just a feeling, it is a specific neurological process. Think of the brain's attention as a kind of spotlight. When we are engaged, that spotlight is pointed outward, focused on the world, on a task, on a conversation. But when we are bored, there is little for that spotlight to land on. So it turns inward. It focuses on the only thing that seems to be changing, the passage of time itself. The brain, without other stimulation, begins to monitor its own internal processes. We become aware of each tick of our internal clock. This state of awareness creates a dense record of moments, making the experience feel long. It is the mental equivalent of watching a pot of water, convinced it will never boil because you are noticing every small change. It is not that time is slower, it is that we are paying it too much attention. Now, let us consider the opposite. What happens when the brain is having an experience that is not boring? This is the second phenomenon, the fast forward of engagement. This is the "where did the time go?" experience. You sit down to play a video game for what you think will be a short while, and when you look up, hours have passed. You have a conversation with someone so engaging that an entire evening disappears. This is the experience of being in a state of flow. Flow is a term from psychology that describes a state of complete immersion in an activity. When you are in flow, your sense of self can fade, and your perception of time becomes profoundly distorted. The brain's attentional spotlight is completely absorbed. All of your cognitive resources are dedicated to the task at hand, whether it is painting, writing code, or being lost in a piece of music. Because the brain is running this demanding program, It has few resources left to dedicate to the background task of timekeeping. The internal clock is effectively quieted. It is not ticking away in the back of your mind, because your mind is somewhere else entirely. You are not logging the passage of minutes because minutes have ceased to be a relevant unit of measurement. This is why engaging experiences seem to make time fly. It is not that time speeds up, it is that the brain simply stops counting. But here is where it becomes even stranger. What about experiences that are not just about engagement or boredom, but about novelty? This leads us to a third and perhaps counterintuitive idea: the vacation paradox. The paradox is this: a week-long vacation often feels like it is flying by while you are on it. But when you look back, that same week can feel incredibly long and full, much longer than a typical week at home. So, which is it? Did time go by fast or slow? The answer is both, and it reveals something fundamental about how memory constructs our sense of the past. During the vacation, especially if it is filled with new and engaging activities, you are often in a state of flow. Time seems to disappear, just as we discussed. But something else is happening. Because you are in a new environment, your brain is cataloging new information. New sights, sounds, smells, and experiences. And it is recording it all. Think of memory as a filing system. A typical week at home does not generate many new files. Monday is similar to Tuesday, and Tuesday is similar to Wednesday. In retrospect, the brain compresses these similar experiences. The week feels short because the memory of it is small and contains little unique information. A vacation is the opposite. Day 1 might be travel day, exploring the city. Day 2 is hiking the mountain, seeing the waterfall. Each of these is a dense, distinct memory file. When you look back, your brain assesses the length of that period based on the asterisk amount of memory it created. Because the vacation week is packed with so many rich, novel memories, the brain concludes that it must have been a very long period of time. It passed quickly in the moment but expands in your memory. This single paradox is a key to understanding one of the biggest mysteries of time perception: the inner workings of time. So, we have established that our perception of time is pliable, easily influenced by boredom, engagement, and novelty. But why? What is happening inside the skull to cause these distortions? The answer lies in a network of brain regions and a cocktail of chemicals that together create our subjective reality. There is not a single time organ in the brain. Instead, time perception is an emergent property of how the brain works. Let us break down the 3 biggest factors at the neurological level. Factor number 1. The dopamine rhythm. You have likely heard of dopamine. It is often called the pleasure chemical, but it is more accurately the motivation chemical. It is involved in reward, anticipation, and crucially for our story, it appears to be a primary regulator of our internal clock. Imagine the brain has an internal pacemaker, a concept from models like the scalar expectancy theory. This is not a single organ, but a process believed to involve oscillating neurons in areas like the striatum. This system is constantly emitting pulses, like the ticking of a clock. When you are asked to judge how much time has passed, another part of your brain essentially counts the number of ticks that have accumulated. This is where dopamine comes in. The speed of this internal rhythm seems to be modulated by dopamine. When you experience something rewarding or new, your brain can get a surge of dopamine. This surge of dopamine appears to speed up the internal pacemaker. It starts ticking faster. So, while your internal clock is racing ahead, objective clock time is still moving at its normal speed. Because your internal clock is ticking so fast, it accumulates a huge number of ticks in a short period. When your brain checks how much time has passed, it sees this large number of ticks and concludes that a great deal of time must have elapsed. This can lead to the feeling that objective time is flying by. Time flies when you're having fun is, neurochemically speaking, a statement about dopamine quickening the pace of this internal rhythm. The opposite is also true. Conditions associated with low dopamine levels, like depression or profound boredom, seem to cause this internal pacemaker to slow. In the same span of objective time, fewer ticks accumulate. Your brain checks the count and concludes that little time has passed, making the present moment feel stretched. Factor number 2. The emotional record. Emotion is one of the most powerful time-bending forces the brain possesses. And no emotion is more powerful than fear. Almost everyone who has been in a life-threatening situation, a car crash, a sudden fall, reports the same phenomenon. Time seems to slow to a crawl. This is not just a dramatic trope, it is a real and documented psychological event. But how does it happen? For a long time, it was thought that in a moment of fear, the brain actually speeds up, allowing us to process information faster. But experiments have shown this is likely not the case. In a study by neuroscientist David Eagleman, people in a state of freefall were shown a special watch with numbers flickering too fast to read normally. The theory was, if their brains had truly sped up, they would be able to read the numbers. But they could not. So what is really going on? The answer seems to lie in memory. When you are terrified, a part of your brain called the amygdala kicks into overdrive. The amygdala is the brain's threat detection center, and when it fires, it commands the brain to record everything. It is a survival mechanism. Your brain switches from its normal mode of memory making to a high-resolution, data-intensive mode. It is like a camera. Most of the time, your brain is recording life at a standard rate. It captures the gist of what is happening. In a moment of mortal danger, however, the amygdala turns that camera up to a higher frame rate. It captures every minute detail. The glint of light on broken glass, the specific expression on a face. You do not experience this slow motion in the moment itself. The event happens at normal speed. The trick happens later, when you access the memory. When your brain plays back that memory, it has so many more frames to process than a normal memory. Because the memory is so dense, your brain makes a logical, but incorrect, assumption. If there is this much information recorded, the event must have taken a very long time to unfold. The slow-motion car crash is an illusion created in retrospect. The brain is a masterful storyteller, and it retells stories of fear with dramatic, slow-motion flair. It is not just fear. Other powerful emotions can also warp time. Awe, for instance, can have an opposite effect. When you experience profound awe, looking at a starry night sky, or the Grand Canyon, people often report feeling like time has expanded. In this case, your brain is so absorbed in processing the vastness of the current moment that your attention is fully in the now, making that moment feel fuller and longer. Factor number 3. The attentional gatekeeper. The final piece of the puzzle is attention. The brain structures involved in how we perceive time are heavily linked to attention and memory, particularly in networks involving the prefrontal cortex, cerebellum, and basal ganglia. Think of the prefrontal cortex as a gatekeeper for the brain's attentional resources. When you are engaged in a task that requires a lot of mental effort, what scientists call high cognitive load, your prefrontal cortex is dedicating all its resources to that task. There is simply no leftover bandwidth to pay attention to the passage of time. As a result, time seems to be compressed. But when cognitive load is low, as when you are bored, that attention has nowhere to go. So, it can turn inward to the most basic process it can find, timekeeping. This is called perspective timing, your estimation of a duration as it happens. Increased attention on the duration itself leads to the perception that it is lasting longer. This is why explicitly counting seconds makes them feel so much longer than when you are distracted. You are forcing your attention to stare at the clock. This network-based model explains why there is not one single disorder that only affects time perception. Because time is woven from the threads of attention, emotion, and memory, any condition that affects these processes, from ADHD to Parkinson's disease, will also inevitably distort a person's sense of time. It is not a single clock that can break, but an interconnected system that can be bent. The architect of time. How memory builds your past. We have arrived at the most quiet and profound part of our journey. We have hinted at it, but now it is time to face the central illusion. You do not experience time directly. What you perceive as the flow of time is almost entirely a reconstruction, an act of creation performed by your memory. Time is less a river you are floating on, and more a story you tell yourself about where you have just been. Let us revisit the asterisk vacation paradox. The key is understanding the difference between two ways your brain measures time: prospective timing and retrospective timing. Prospective timing is your judgment of time as it unfolds. It is what you use when you are waiting and thinking, how long has it been? This is the type of time perception dominated by attention and dopamine. If you are bored, prospective time drags. If you are engaged, it flies. Retrospective timing is your judgment of how long an event lasted after it is over. It is when you look back at your vacation and think, how long did that feel? This is where memory becomes the sole architect. Retrospective time is based on the number of new memories you formed during that interval. This is the simple explanation for the paradox. During the fun-filled vacation, your perspective sense of time is short, it flies by. But because every experience is new, you're forming a huge number of distinct memories. Later, when you look back, your brain examines this vast library of memories and concludes the vacation must have been very long. Conversely, a routine week at home feels normal or even slow prospectively. But because you form very few new memories, the entire week gets compressed in retrospect. When you look back, there is not much there to see, so it feels like it vanished. Your memory literally rewrites your temporal history. This mechanism is also the most compelling explanation for why time seems to accelerate as we get older. Think about your childhood. Almost everything is a first. Your first day of school, your first bike ride, your first time traveling alone. Your brain is in constant novelty detection mode, creating an incredibly dense tapestry of memories. This is why a childhood summer can feel like a lifetime. The sheer volume of new memories expands that period in retrospect. As you enter adulthood, routine takes over. You drive the same route to work, you do similar tasks each day. The number of firsts dramatically decreases. Years start to feel similar. Your brain, in its efficiency, begins to compress these routine years. Fewer new memories means a shorter retrospective duration. The years from 30 to 40 might create fewer unique memory files than the single year you were 16. It is not a tragedy, it is a feature of how memory works. Time is not speeding up, your record of it is just becoming more predictable. Scientists have demonstrated this with an experiment called the oddball effect. They show participants a series of identical images, then suddenly flash one different, oddball, image for the exact same duration. Almost universally, people report that the oddball image stayed on the screen for longer. Its novelty captured their attention, forcing the brain to dedicate more processing to it. This created a richer memory trace, which the brain misinterpreted as a longer duration. The brain equates memorable with long. It is a fundamental equation in the calculus of psychological time. When the perception of time is altered. For most of us, these time distortions are fascinating quirks of cognition. But for some, this distortion is not a quirk, it is a profound alteration of experience. When the mechanisms of emotion, attention, and memory are disrupted, the perception of time can become a prison. Nowhere is this more evident than in clinical depression. Psychiatrists consistently report that one of the most common subjective complaints from depressed patients is that time seems to be crawling or standing still. This is a profound alteration of their temporal reality. We can now understand this on a neurological level. As we discussed, dopamine plays a key role in the speed of our internal clock. Depression is often associated with a dysfunctional dopamine system. This can lead to a chronic slowing of the internal pacemaker. For someone with severe depression, their internal clock might be ticking at half speed. As a result, a single day can feel like a week. The future can feel impossibly far away, and the present becomes a heavy burden. This temporal distortion can exacerbate feelings of hopelessness, creating a difficult loop where the feeling that time is stuck makes them feel more depressed, which in turn further slows their perception of time. It is not just depression. Many other conditions are linked with distorted time perception. People with anxiety often report the opposite, a feeling that time is speeding up. This may be linked to a state of hyperarousal, where an overactive amygdala and constant worry effectively speed up the internal clock. Conditions that affect the brain's core timing circuits in the basal ganglia and prefrontal cortex, like Parkinson's disease or schizophrenia also cause issues with judging time intervals. Even ADHD which is fundamentally a disorder of attention and dopamine regulation, has a strong link to altered time perception, making it difficult for individuals to wait for delayed gratification because the future feels disproportionately far away. Finally, we can observe the direct impact of psychoactive substances. It is common knowledge that different drugs alter the sense of time. Stimulants often work by increasing the amount of available dopamine in the brain. This, as we now know, speeds up the internal clock and makes time feel like it is flying. Sedatives can slow down neural processing, leading to the impression that time is stretching out. These substances provide a direct, chemical confirmation of the models we have been discussing. They are, in effect, a way to directly influence the brain's internal clock. Understanding these phenomena validates the experiences of many people, showing that their feeling of time being wrong is a real consequence of their brain's altered neurochemistry. The architect in the mind. So, where does this leave us? We have journeyed through the quirks of daily life, into the wiring of our neurons, and through the archives of our memory. The conclusion is as staggering as it is quiet. Time, as you experience it, is not a fixed, external reality. It is a story, written and directed by your own brain. The fundamental glitch is not in time itself. It is a feature of our own perception. To summarize, your subjective experience of time is a construction, built from three primary ingredients: the chemical wash of emotion particularly dopamine and adrenaline, the focus of your attention, and, most importantly, the rich and unreliable tapestry of your memory. Your brain has an internal rhythm that speeds up with excitement and slows with boredom. It has a survival mechanism that pads the memories of fearful events with extra detail, making them seem longer in retrospect. And it uses the volume of new memories you create as its primary ruler for measuring the past. This might sound as if you are living in a hallucination. In a way, you are. But this knowledge is not a reason for despair. It is a user manual for your own perception. Because if your brain is the one creating time, then you have more influence over it than you might have thought. You cannot stop the objective clock from ticking, but you can change how you experience those ticks. If you feel that time is slipping through your fingers too quickly, the solution is not to have more time, but to create more memories. Break your routine, seek out novelty, learn a new skill, travel to a new place, have a conversation with a stranger. Fill your days with firsts. By creating more unique memory files, you will retrospectively lengthen your life. You can make your years feel as full as your childhood summers once did. And if you want to slow down the present moment, you can do that too. The practice of mindfulness is, at its core, an exercise in temporal perception. By deliberately focusing your attention on the sensory details of the now, the feeling of your breath, the sounds around you, You are gently fighting back against the brain's tendency to wander or compress time. You are anchoring yourself in the present, making it feel richer and more expansive. Time does not glitch. Our brain does. But that glitch is also what makes us human. It allows us to feel the thrill of a moment that flies by and to savor the memory of a day that feels like a lifetime. We are all time travelers, constantly moving through a past and present of our own creation. The trick is to become a conscious one. So, what about you? What is an experience that always seems to alter your sense of time? Is it getting lost in a good book, a quiet weekly meeting, or a vacation that felt like it lasted a month? Feel free to share your own time glitch in the comments below. Time doesn't end, it just forgets to tick. What if the story of the universe does not end with a sudden, violent event, but with a quiet that lasts forever? Not in millions or even billions of years, but on a timescale so vast that the concept of a year loses its meaning. This is an exploration of that future, a state known as the heat death of the universe, and how time itself might not stop, but simply forget how to move forward. It is not a story of destruction, but of fading. A slow, cosmic exhale into a darkness and a quiet so complete, it will last for an eternity we can barely begin to imagine. Imagine a hot cup of coffee left on a table. The heat is concentrated, a small pocket of order in a cooler room. But over time, that heat will always spread into the surrounding air, until the coffee and the room are the same temperature. You will never see the room grow colder to spontaneously heat the coffee back up. The flow of energy only moves in one direction, from concentrated to diffuse, from order to disorder. Physicists call this principle the second law of thermodynamics, and this measure of disorder, entropy. Our universe follows the same law. It began in an incredibly hot, dense, and low entropy state, the Big Bang. That initial order has been unwinding ever since. The differences between hot and cold, dense and empty, are what allow anything to happen at all. They allow stars to form, chemistry to occur, and life to exist. But the second law is a guarantee that this state of activity is temporary. Eventually, all energy will be so evenly distributed that no work can be done. Nothing can happen. This is the state of maximum entropy. This is heat death. This is a journey through that process, a quiet exploration into the deep future, to witness the slow, steady fading of the cosmic light. Welcome to the Sleepy Scientist. If this kind of calm exploration helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from, as we look toward the end of time together. The end of the Stelliferous Era. We live in a remarkable period, the Stelliferous Era, the Age of Stars. For nearly 14 billion years, gravity has been patiently gathering clouds of gas, compressing them until their cores ignite, giving birth to stars. These stars, from brilliant blue giants to our own quiet sun, are the engines of the cosmos. They create heavier elements and scatter them through space, providing the raw material for planets, and eventually, for us. But this long season of creation relies on a finite supply of fuel. The universe is already past its peak star-forming period. The rate of new star birth is slowly declining, like a fire that has already burned through its most accessible logs. In about 100 trillion years, this process will have almost entirely stopped. The vast clouds of gas will either be used up or spread so thin by the universe's expansion that they can no longer collapse. The stellar nurseries will go quiet. The universe will then be home only to the stars that already exist, and they, too, are temporary. The most massive stars burn out in only a few million years. Stars like our Sun last for around 10 billion years before becoming faint white dwarfs. The last lights in the cosmos will be the red dwarfs. These are the frugal embers of the universe, sipping their fuel so slowly they can burn for trillions of years. For an immense stretch of time, these faint red points of light will be all that remains in an increasingly dark cosmos. But even they cannot last forever. One by one, over a span of up to 100 trillion years, the last red dwarfs will exhaust their fuel. They will not explode. They will simply fade out, their nuclear fires extinguished, becoming cold, dead objects called black dwarfs. With their passing, the stelliferous era will be over. The great age of light will have given way to a universe of remnants. As this happens, the universe itself will be slowly unraveling. The accelerating expansion of space, driven by dark energy, will stretch the distance between galaxies. Eventually, all other galaxy clusters will recede from our own, moving away so fast their light can no longer reach us. They will disappear behind a cosmic horizon, leaving our local group of galaxies as an isolated island in an endless void. Within this island, orbits will begin to decay. Over trillions of years, gravitational encounters will gently nudge stars and their dead planets, flinging some into the intergalactic darkness and causing others to spiral slowly toward the supermassive black hole at the galaxy's center. The once majestic structures of galaxies will dissolve into a disorganized, ghostly haze. The degenerate era. Welcome to the degenerate era, beginning roughly 100 trillion years from now. The name does not suggest a moral failure, but a state of matter. Degenerate matter is what remains when a star's internal fire goes out, and it is supported only by quantum mechanics. The universe is now a quiet, dark space, populated by these stellar remnants, black dwarfs, neutron stars, and black holes. The sky, if there was anyone to see it, would be almost entirely black. The only light might come from rare collisions between two white dwarfs, which could, for a moment, create a new, temporary star. But such events would be extraordinarily infrequent, a single spark in an ocean of darkness. Planets, if they survived their star's death, would continue to orbit these cold husks, frozen worlds in an eternal night. But even these structures are not permanent. The universe has another, much slower process of change, proton decay. Many theories in particle physics suggest that protons, the building blocks of atoms, are not truly stable. They are predicted to have an incredibly long but finite lifetime. Over unimaginable timescales, perhaps 10 to the power of 37 years or longer, the very substance of matter will begin to dissolve. Protons will spontaneously decay into lighter particles. It would be like watching a stone monument slowly return to sand, not from erosion, but from its own atoms coming undone. The cold, dead stars will not just cool, they will evaporate. A white dwarf will slowly dissipate into a faint whisper of radiation. A frozen planet will simply vanish, its matter dissolving atom by atom. This process erases the last familiar structures. By the time it is complete, the only organized objects left in the universe will be the black holes. The black hole era. We now enter the longest chapter in the universe's story, the black hole era. Beginning around 10 to the power of 40 years from now, the universe is an almost perfect vacuum, vast and cold. The only significant objects that remain are black holes, the gravitational survivors of the previous eras. For a long time, it seemed they would be the final state of the cosmos, eternal prisons of matter and energy. But in 1974, Stephen Hawking made a profound discovery by combining general relativity with quantum mechanics. He realized that black holes are not completely black. Due to subtle quantum effects at their event horizons, they should emit a faint trickle of thermal radiation. This process is now known as Hawking radiation. It revealed that black holes, too, are temporary. The vacuum of space is not truly empty. It is filled with virtual particles that appear in pairs and almost instantly annihilate each other. If a pair appears at the very edge of a black hole, one particle can fall in while the other escapes, carrying a tiny amount of energy away. Because mass and energy are equivalent, this means the black hole is slowly losing mass. It will, ever so slowly, evaporate. The process is fantastically slow. A black hole with the mass of our Sun would take around 10 to the power of 64 years to disappear. The supermassive black holes at the centers of galaxies could last for a Google years. 10 to the power of 100 years. A number so large it resists comprehension. As a black hole loses mass, its temperature rises, and the evaporation speeds up. In its final moments, a black hole that has been shrinking for eons will release its remaining mass in a final, quiet flash of energy. These will be the last significant events in the history of the universe. One by one, every black hole will evaporate until the last one disappears. With its passing, the black hole era ends. The last organized structures are gone. The dark era. We have now arrived at the final state of the cosmos, the dark era, after 10 to the power of 100 years have passed. The universe is a vast, ever-expanding sea of near-nothingness. It is populated only by a diffuse, incredibly thin gas of photons, neutrinos, and other fundamental particles, the final debris of everything that ever was. These particles are so far apart they will almost never interact. The temperature of the universe will have approached, but never quite reached, absolute zero. The universe has reached a state of maximum entropy. It is in perfect thermodynamic equilibrium. This is the heat death. Not a fiery event, but the ultimate, eternal cold. It is a state where nothing happens. No change. No processes. The great cosmic engine has wound down. The universe is cold, dark, and empty. And it will remain this way, forever. An infinite expanse of stillness. Time doesn't end, it just forgets to tick. In this final state, what happens to time? Our entire perception of time is based on change. We experience it as a sequence of events, a progression from cause to effect. The reason we remember the past but not the future, the arrow of time, is tied directly to the second law of thermodynamics. Time flows in the direction of increasing entropy. A broken egg is a state of higher entropy than a whole one. We see eggs break, but we never see the pieces spontaneously reassemble themselves. That irreversibility defines the forward march of time. But what happens when entropy can no longer increase? When every part of the universe is the same, and there are no energy differences left to drive any process. At this point, the second law becomes meaningless. There is no longer a defined direction for the future. If time is defined by the progression of events, and no events can ever happen again, then what does time measure? It would not end, in the sense of ceasing to exist as a dimension. The time coordinate would still stretch on toward infinity. But it would become irrelevant. It would be an infinite, now, a static existence without a past or a future. Imagine a perfectly still, unchanging photograph. Time may pass for the photograph, but nothing in the photograph changes. The universe would be frozen. Time would still be there, but it would have nothing to do. It would have forgotten how to tick. The alternatives, other possibilities. The heat death is the most likely scenario based on what we know today. But our understanding is incomplete, and science continues to consider other possibilities. One is the Big Rip. This imagines that dark energy is not constant, but grows stronger over time. If so, the expansion of the universe would run away with itself. In perhaps 22 billion years, it could become strong enough to tear apart galaxies, then solar systems, then planets. In the final moments, it would overcome the forces holding atoms together, and spacetime itself would be torn apart. Then there is the possibility of a Big Crunch. For a long time, this was a leading idea. If the universe had enough mass, gravity could eventually halt the expansion and reverse it. The universe would contract, galaxies rushing back together, until everything collapsed into a singularity, similar to the one it began with. This idea has become less likely with the discovery of accelerating expansion, but some recent models suggest it might still be possible, perhaps opening the door to cyclical universes, in an endless series of birth and death. And finally, there is the most unusual idea of all. Poincaré recurrence. This theorem suggests that in a finite, closed system, given an almost infinite amount of time, it will eventually return to a state very close to its original one through sheer random chance. After a timescale that makes a Google years seem like an eye blink, the scattered particles of the dark era could, in theory, spontaneously arrange themselves back into a low entropy state, triggering a new Big Bang. The odds are so small as to be practically impossible, but it remains a quiet possibility at the farthest edge of theoretical physics. This long journey leaves us here, on a small planet, in a quiet corner of one of trillions of galaxies, in a universe that is still in its bright and energetic morning. Our existence is made possible by the very processes that will one day lead the universe to a silent end. We are a momentary flash of complexity, a fleeting thought in the mind of the cosmos. Faced with the unimaginable stillness of the deep future, our own existence can feel small. All our achievements, our art, our struggles, all will eventually be erased, dissolved and radiated away into the quiet of the dark era. But perhaps that is the wrong way to look at it. The fact that the universe will one day fall silent does not diminish the beauty of its current state. Knowing that a fire will eventually go out does not stop us from enjoying its warmth while it lasts. We are living in the brief, glorious age of stars. A time of creation, complexity, and consciousness. We are the universe's way of witnessing itself. The story of the heat death is not just a bleak forecast. It is a quiet reminder of how precious the present moment is. It tells us that order, complexity, and life are the rare exceptions. The universe, for most of its past and for almost all of its future, is and will be a cold, empty place. But not now. Now, it is full of wonder. And we are here to see it. The knowledge that the light will one day fade should only make us appreciate its brilliance all the more. So what do you think? Is the silent, eternal fade of the heat death a strangely peaceful prospect? And what does it mean for how we see our lives right now? If this quiet exploration of the cosmos has helped you find a sense of perspective, consider liking the video and subscribing for more journeys into science. Thank you for watching.